開会の前にですね、ちょっとアナウンスというかですね、どうぞどうぞ。本日は、ちょっと長丁場になります。それで、最初にここで、ミーティングがあって、その後、昼間にですね、ルナテラスの見学があります。そこでランチをして、はい。英語、OK。Sorry, sorry. This is International Symposium. I have to introduce yourself. Today we will have a session here from now and 12 o'clock, and then we will move to the Luna Terrace, and then we have a lunch together, and then we will have a next session. After the next session, we have to gather and taking the bus to the sand dune. And after the sand dune, and there is museum, but somebody who want to join the outreach session, who is Japanese, please join to the outreach session. However, our official program will be after the museum, there is a farewell party, and which will be held in the different place. And you have a dinner, and also you have a party. But before starting, we would like to introduce one space artist, Arisa Kuroda. Yeah, she will be reporting today's fall symposium, including our activity, and then she will post officially to her YouTube channel. So please be careful what you are talking to her. It is very important person. But she will not intervene this session, but she will be speaking in Japanese in outreach session. じゃあよろしくお願いします。Okay, so let me first introduce. Okay, thank you for gathering today. It's Tottori University. It's a special session. And this session, we will focusing on the ecosystem and space. University of Tottori is very famous for improving the not desirable environment to the favorable environment by cultivating tree in the desert zone. And this technology is very, very well known and established since 1990, because many, many countries are sending trainees here. And then there is an official program of JICA and supporting and that kind of experience. And this will enriching the space environment. When we think eternal settlement in the space, you have to improve the rigorous and harsh environment to the favorable environment. And that technology from the University of Tottori will be giving a specialized benefit for the space environment. Okay. So I would like to seek for the Professor Tsujimoto, but Tsujimoto sensei is where? Oh, here. Okay, so let me introduce Professor Tsujimoto, who is a director of the Arid Land Research Center. He is also a host of this session. So please, Professor Tsujimoto, please have an introductory speech. Thank you.
Expect great nature, sand dune, beautiful starry sky, or something like that. And also people come here to eat very fresh, nice seafood, meat, vegetables, milk, mushroom, and etc. And we have 10 natural onsen. You know what is onsen? Onsen is a natural hot spring. People want to refresh taking this natural onsen. Okay? Especially in Tottori Sand Dune is a very famous, and more than a million people come here annually. And this is a part of San-in Kaigan National Park of Japan, and also UNESCO's San-in Kaigan Geopark. And also this is a natural monument. And so many people come here and climb up the sand dune and see the beautiful ocean, Japanese ocean, and ride the camels and feel they come to the Arabic desert. And yeah, this is a Google map of Tottori city. Yeah, you are here now. Okay, and maybe many of you stay around Tottori station. And you can see Tottori Castle on the mountain. And the Tottori University main campus is here. And airport and port. Yeah, this is a typical local city in Japan. But the exception is here. This is Tottori Sand Dune. Many people come here, but before the sand dune distribute to these area, very wide, very wide. Yep. So first, the Tottori College of Agriculture established a research station here near airport. Yeah, the place of airport was sand dune, a part of sand dune, and developed, started the research combat sand dune. Okay, and later, this place was the university, or actually the Japanese government established the Sand Dune Research Institute. Before the World War II, this place was an army camp. So after finishing the war, this place was released and the university got part of Sand Dune and started to establish, work of Sand Dune. Okay, anyway, but this place is not the desert in Arabic country, because we have much rain. Here we have about 2,000 millimeters of rainfall. Yeah, so this is a wetland, actually. But the reason why sand dune appear is here is that because we have very strong wind in springtime and also wintertime. Okay, yeah, here you can see this movie.
Yes. In wintertime, springtime.
This kind of sand movement by wind, and also people enjoying this sand. Yes, but it's a very big problem when we cultivate a plant. This is my wheat plant. You see the this kind of sand flying. Very difficult to cultivate. This place make farmland. Okay, how to go to the next. Okay, so in 1923, just 100 years ago from now, one professor in a Tottori College of Agriculture established established an experimental station, and he made a hedge of bamboo and set this hedge almost all the area of the sand dune and try to stop the sand movement and transplant pine tree and other trees and make this place forest. You see, this is a picture taken 1952. We are now here. We are in the mid of sand dune. But after transplanting, this area become very green. So once sand could be stopped successfully, The next is how to develop this land for agriculture. I said that we have much rainfall, but we had, the farmer that time had a very big problem of water. See, different from soil. Sand cannot hold water. So that time the farmers took the water by this kind of woody bucket and distributed water. It was very, 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 very hard work. Yeah. So this institute transfer the sprinkler irrigation system. Yes. So these farmers released from this very hard work. Okay. And next is what crop they should cultivate. What crop can adapt to this kind of harsh environment? People tested tulip or something, but finally they found that rakkyo is a very special kind of onion, good for pickle. Yeah, they found that this is a very nice crop for this kind of environment. Okay, here I want to summarize the history of the sand development and sand development of sand dune. In 1923, 100 years ago, Oyama Sand Dune Research Experimental Station was established. And 1949, after the war, this area was given by the government, and Sand Dune Research Center of Tottori University was established. And 1990, the institute organized, reorganized. Yeah, because our issue was solving the local issue, but gradually our mission, our target changed from our local sand dune to the international desert. And they changed the institute. They reorganized the institute and renamed the Sand Dune Research Institute to Erie Durand Research Center now, 30 years ago. And this year, we are going to celebrate 100th anniversary of dune research next week. Arid Durand, yes, it's very largely distributed, and it is said that about 40% of the land are defined as arid land, where 1/3 of the population in the world living. And sand dune are divided, classified into these 4 groups: hyper-arid, like in Sahara Desert, and arid, semi-arid, and dry subhumid. So about half of the United States, American continent, and also some of the Europe are also regarded as classified as arid land. Because we changed to the from sand dune development, our target from sand dune to arid land research center. Now it is a center of excellence of this kind of research, and our government install many excellent facilities, equipment here. I will show some of the equipment. This is the butterfly windmill, and this is dome. And you can see the here. You can see a small museum showing our performance. And this museum is open today. So during break time, you can visit here. And this one. This one is we call it rain out shelter. When rain starts, this big roof move and cover the plant and make the atmosphere like desert. Okay, and this is a genetic modification plant laboratory, because GM plant is very important to cultivate in such an area. So we have this kind of greenhouse, and also as shown here, last year we developed the lunar terrace. This was developed by Tottori Prefecture. Yes. And as you see here, we are testing lunar rover. Okay, so Arizona science is not the same as the space science, but I think that the Arizona science is a part of marginal land science. So the direction of Arizona science is similar to that of space science. So I hope that in this Tottori event, we can discuss and we can find the good hint to develop the space village. So thank you very much. Please enjoy this meeting.
Thank you, Professor. This is an announcement that the University of Tottori is located one of the most fascinating place. I think inside of this building is actually a part of the sand dune that we will visit a very important place during the lunchtime. So please follow the guidance of Professor Tsujimoto. Thank you very much, Professor Tsujimoto. Okay. So now, actually, we were supposed to having a greeting from the governor. However, due to extraordinary schedule of the governor, he cannot come here. However, we have actually many support from the Tottori Prefecture, including during the lunchtime and also the outreach session, and where the representative of the Tottori Prefecture will say greeting, a short greeting in Japanese, and I will translate at that time. This is an apology from myself. Okay, now let's move on to the introduction of the Moon Village Association. So the Moon Village Association is a non-profit but international organization which having continuously support for the space migration. And the International Moon Day was established and recognized by the United Nations. And today we have our vice president of the Moon Village Association. John, are you ready to come in here and introduce yourself? Okay, please come. Okay, please, can you say hello? So he will give a talk, but are you ready to share his screen? And who can give a, can you do?
So it's good. Good morning. It's very nice to be here in Tottori. I know that the president of the Moon Village Association, Giuseppe Ribaldi, is very sorry that he's not able to be with us this week. Are you ready for the slides?
Slides?
Okay. Not yet. Okay. So I'm going to share with you just the slides that I used yesterday at the outreach event in Karashiki. And if you would be so kind as to go forward. Keep going. One more. This one. So the Moon Village Association is a non-profit organization founded in 2017 and is incorporated in Vienna, Austria. We have more than 600 people around the world who are working with the Moon Village Association, and some 33 institutional members. Those are businesses, universities, non-governmental organizations, and they represent a very diverse array of technical and scientific and interdisciplinary fields. The purpose of the Moon Village Association is to promote international discussions and progress towards the vision of humanity on the moon. There are a great many programs and organizations having to do with lunar science. There are, of course, national space agencies and government institutions that coordinate with each other on specific programs, just as is the case with the International Space Station and the more recent Artemis Accords, in which the US and Japan and many other countries are signatories to agreeing to cooperate on certain standards of behavior having to do with the government lunar exploration and utilization activities. But the Moon Village Association is open to everyone. It's open to governments, it's open to universities, it's open to companies, entrepreneurs, individuals, and it is a forum, a way to become involved in the expansion to the moon, the development of the moon, the protection of the moon in terms of its the artifacts that are there that have to do with the culture of the moon, or the science of the moon. And so we believe the Moon Village Association is rather unique in that regard. And we work with other organizations, for example, For All Moonkind. That is a non-governmental organization that seeks to preserve the cultural heritage and the environment of. We work closely with them, and there are a number of others. And so we have a number of projects and different working groups. For example, the GEXLA, which is a very challenging acronym. It stands for Global Expert Group on Sustainable Lunar Activities. So how to translate, for example, the United Nations Sustainability Goals to the moon. We are an observer of the United Nations Committee on the Peaceful Uses of Outer Space. We are a member of the International Astronautical Federation, and we are involved in many technical activities. This workshop and symposium is our flagship activity each year. And each year, beginning in 2017, it is in a different location around the world. We started out in Strasbourg, in France, at the International Space University, 2017, and then 2018, we were in Los Angeles. 2019, we were in Tokyo and Kyoto at the Tokyo University of Science. I know several of you are from there here today. And then, of course, in 2020, COVID. And so 2020, we were only online. 2021, we thought we could get things going, but then, of course, there was a surge of COVID cases in the fall and virtual. And last year, we were again in Los Angeles, and that was where the proposal from Japan, led by the JAXA and by Hinetani Sensei and others, made the proposal and was accepted to be the host and the location for the 2023 7th International Workshop and Symposium of the Moon Village Association. So you can go forward one. That's okay. You can go forward one. He's trying to make me go quicker because I'm running out of time. I've used up too much time. I'm sorry. But just wait. Just wait. ちょっと待ってください. I would like to encourage all of you to become involved in the activities of the Moon Village Association. And one of these, which we mentioned at the first part of this meeting in Karachi, is the annual International Moon Day, which is a global celebration of when humans first went to the moon on July 20th, 1969. And this was a global holiday and celebration established by the United Nations several years ago. And we've had now 2 International Moon Days since it was created. The first one was in we have a main central event, and then we have regional events all over the world. The main central event in the first one, so 2021, was in Huntsville, Alabama. And Richard Fisher is a member of the Moon Village Association, and he was instrumental in working with a local college, Drake State Technical College, in making the first International Moon Day main event happen. It was very exciting. We had a number of people from the NASA Marshall Space Flight Center participating, and including people who worked on the Apollo program back in the 1960s. And then the second one, this past summer, which was in Korea, South Korea. So I will encourage the people who are here and who are interested in celebrating the moon to get involved in the 2024 International Moon Day. Local events can be organized. And our theme this year is illuminating the shadows. And this is both the literally idea of going into the permanently shadowed regions, looking for resources, trying to learn the past history of the moon and so on in the solar system, but also illuminating knowledge as a metaphor, trying to find new knowledge and new understanding of our future on the moon. So please join us in this activity. Next, please. And with that, I will close and just say welcome to this final day of the Workshop and Symposium 2023. And oh, I should mention, and I should mention that at the closing yesterday, if you were not there, we announced the location of next year's 2024 Workshop and Symposium. It will be in Luxembourg, and will be co-hosted with the Luxembourg Space Agency. And of course, at Luxembourg, there's a huge focus on space entrepreneurship and ventures, new technologies. And so we hope that many of the Japanese companies and entrepreneurs that have been here this week will join us next year. Maybe the first week in December, it's still to be decided, but will join us next year in Luxembourg. Okay, that's all. Thank you so much for your attention.
Are you going to show the video from the Giuseppe? No. Giuseppe, message from Giuseppe? No, it's not this. Okay. No, okay. Thank you. Thank you very much, Vice President John. And then we will have a speech from the local organizer. It's a private company, Apirapo. Dr. Tanaka, are you? Oh, you are here. Oh, I didn't find you. Okay. So he's actually coordinating almost everything, including the outreach event and all logistics. So he's a super person and super talented person. And the key person who introduced the space industry here. So let me introduce him again. And if you can invite him. Okay. So please, Dr. Tanaka.
Thank you for Yamashiki Sensei. So, hi, I'm Katsuaki Tanaka, the CEO of Amirapo company. We, Amirapo, are creating lunar development industry in Tottori, And we are aiming to develop a demonstration field that's simulating the lunar environment with Tottori government. So today I'd like to talk a little bit about activity for it. Okay. Sorry. So this is my career slide. Sorry for this is small, but I am a space robotics engineer, and I was in iSpace and mainly developed a mobility system of lunar rover. And at the same time, I started a company that creates a space experience contents by virtual reality with the aim of expanding the space industry market. In 2016, iSpace Team Hakuto conducted a roving test of lunar rover in Tottori-san dunes. I was also involved in the experiment as one of the engineer, and at that time I realized that this kind of natural environment might be worth using a demonstration field of the lunar surface. So Tottori-san Dons has an extremely rich natural environment, and it has a similarity to the lunar surface, I think. Upper side of the photo shows the lunar surface on the moon, and the bottom side is a photo shows Tottori-san Dons covered with fine sand. There is also slope with a large slope called Umanose in Tottori-san dunes. Such similarities can be especially useful when testing lunar vehicles. So in order to branding this unique environment and make it known to many people, we create an astronaut activity by virtual reality and AR system that resembles Tottori-san dunes at the surface of the moon. So I want to show a short video. So this videos of astronaut activity by virtual reality and AR on Tottori-san dunes. So tourists can wear the AR glasses and experience creation of the lunar city as if they were astronauts. So you can experience it from 7 p.m. today after farewell party, so reception. So if you are interested, please come and experience. Okay. And we are very grateful that this kind of activity is so rare, even in the world. So this event was featured in many famous media in Japan. So thanks to the media coverage, so Tottori-san dunes have been able to attract even more people attention. So we are aiming to create a world-leading lunar surface development base from Tottori-san dunes. We are trying to use Tottori-san dunes as a simulated lunar surface on the ground and as a test field for various future spacecraft. We believe that by actually taking the spacecraft tested here to the lunar surface, we will be able to understand the relationship between the lunar surface and the Tottori-san dunes. It is important to understand the correlation between the Tottori-san dunes and the lunar surface. By realizing this as soon as possible, it will be an important base that attracts many researchers from all over the world. So in response to this request, Tottori government created the first demonstration field within Tottori University in this July. The field size is 50 square with slope up to 20 degrees. on flat ground, there is a zone where you can travel up to 100-meter long. Today's round session will include a tour of lunar terrace and rover demonstration. Please looking forward to it. By using this demonstration field, two methods have been developed to predict the behavior on the lunar surface. One method is metaverse, which allows experiment on the moon surface in digital field. The other is Tottori sand dunes, and also the ground test is which allows experiment on the lunar surface in analog space. So we believe that by sharing the data between these three among the three environment, we can accelerate the experiment on the lunar surface on the ground. And so part of these efforts, we have begun the collaboration, collaborating with the Tottori government to collect the data on the Tottori sand dunes themselves. So we are able to provide a multiple data set of the Tottori sand dunes. For example, we already get 3D point cloud data. This is 6 billion points of the size. And also, we also analyzed, have analyzed data and particle size analysis and chemical component analysis, and also the mechanical things also we already get. So we try to get this kind of data many times and try to able to provide researchers to able to use this kind of data. And finally, so we also support the students group in their rover development and the experiment. These two organizations will be holding the demonstration as a demonstration field during the lunch session. So please looking forward to it. And thanks to this field, I hope that a number of players in various lunar surface development will continue to increase in Japan. And also, still being finalized, we plan to use this field to host rover competitions with various players. We will hold the first rover tournament in the spring of 2025. And creating an environment where a variety of players can compete on this field. We aim to make this tournament a world tournament in the future by inviting many players, not only from Japan, but also from the overseas. Now we are also looking for some sponsors and cooperation sponsors. So if you are interested, please let us know. Okay, so please enjoy the lunar development in Tottori. Thank you so much.
Thank you very much, Dr. Tanaka. So the next, I would like to introduce myself, but before, I would like to introduce our local organizing committee, actually, Eizo Nakamura-san. And important person is Mira Sensei is there. Mira Sensei is sitting in the behind, but he is actually one of the most important person for organizing in this Tottori event. He used to be an associate professor here, and now he moved to Jackson and introducing everything. And Eizo Nakamura Sensei, he's a chairperson of the local organizer. I think he has a kind of a health problem today, so he cannot attend today, but he is a very big organizer for this event. And Inatani Sensei is here. Inatani Sensei, where is Inatani Sensei? He's also sitting in the back. But he's like most powerful and authority for us. So we are following what his guidance, everything. So, okay. Yeah, no. So, and Mrs. Onuki, Onuki-san, she's a big she's actually coordinating financial part of this event, actually collecting and requesting, and also she has achieved the biggest companies donation from all over the world. And also we have a message from Naoko Yamazaki, she's an astronaut, and also the Terada from Kyoto University. Okay, so I am one of the actually proposer of the session, and together with Tsujimoto Sensei, and also the okay, so the president of Okayama University changed, but it was before. So and also I would like to introduce myself, and what it is a very important theme of the session. So let me just introduce what we are going to talk today's session. Okay. So the three essential core concepts, and I'm sorry, I put the Japanese because many Japanese audience is here and to comprehend and facilitate the interruption of the concept. Okay. So what is so we propose the three essential core concepts and establishment of the Terra window for the space migration. It's a kind of a new concept, but of course, this concept was developed following what we have developed before. So first, I would like to introduce SIC Human Spaceology Center and three essential core concepts, and core biome, and introduction of the space camp in Biosphere 2, and core technology, core society, and also finally, the terraforming Mars and the Terra window concept. But okay, the first of all, one of the hosting organization is the Kyoto University SIC Human Spaceology Center, was established in 2020 together with those members, but exclusively Professor Takaodoi is a former astronaut who gave a talk yesterday in Okayama session. And also we have a visiting professor, Vladimir Airapedian from the NASA Goddard. He is coming in Japan next March. He was giving a lecture. And also Professor Inatani is also, probably he is forgetting, but he's also a visiting professor of Kyoto University. Okay, and Professor Inatomi from JAXA, and Professor, visiting Professor Sato Tatsuhiko. And Naoko Yamazaki, she is also associate professor, and Takuya Ono, who will give a talk and the outreach session. So we have published a Japanese book. This is a Japanese book. I'm sorry, I cannot give this today, but it's about the human spaceology and three essential core concepts of the space migration, just published in this July. So hopefully we have our English version. Okay, what is the three essential core concept? We have determined the core biome. This is a focal discussion today. It's a necessary biome, which represents a terrestrial biome, and core technology and core society. And what is this? So please think about the Earth first. So in the Earth, if you are facing the Earth, assuming that you are alien and visiting the planet Earth and visiting our solar system from the outside of the solar system, and you found a blue marble, right? And it is covered 70% of the ocean, and you have a cloud and you have land. And what you will see is a 70% of the ocean. So it's an ocean planet. It's almost ocean planet. And you will find the land. In the land, you have a desert, but you have a vegetation. So vegetation occupies a very big portion of the terrestrial world. So you can see from the space. But the important thing is Earth's environment is surrounded or supported by the ocean and the vegetation. So the presence of the ocean and vegetation is essential. That we will call it a natural resources. It's a core biome concept we have determined: ocean and forest and soil. And then let us think about how can we live in the modern society. So to establish our daily life, what we will need. We will need food, and we will need water, plenty of water. But please think about water, because first, when we talking about ocean, it's a saline water. You cannot drink the water from the ocean directly because it's a high salinity. But what we request is fresh water. Fresh water doesn't have a salinity, but fresh water is coming thanks to the presence of the hydrological cycle. So we have a hydrological cycle, so we have rainfall, so we can drink the fresh water. So we are a species which can live only in the surface of the land. We cannot live under the ocean. So we will discuss about ocean today, very detailed. But what we will need fresh water and food and energy. Why we need energy to sustain our society, sustain our civilization. So the life supporting lifeline structure, we can determine it's the water and also the energy and food. But if you move to the next different planet, we will need, of course, it's oxygen. Because the oxygen, we have plenty amount here in the Earth, so we don't care oxygen, whether you have oxygen or not, but the oxygen is an essential element, but we are forgetting. But after establishing, after securing the presence of the water, fresh water, and food and energy, then we can think about the building the social infrastructure, including, so we can start discussing about politics and also the economy and community. But before not having secured water and food, who's gonna having a economy? So economy is after the basis of the presence of the secured food and water, right? So most important thing is here. So when we think about moving into the different planet, what we will need, of course, most important thing is a lifeline infrastructure. So we need a water in the space, we need air and food. Of course, energy. Energy is coming from the sun. But then let us think again about our background, because in the Earth, water, where water coming from? They're coming from the rainfall. It's a hydrological process, but that water is supplied from the ocean. And if we move to the moon, do you have ocean? No ocean, right? So do you have a supply of the water? No supply. So the all lifeline in structure in the space should be prepared by the human. And that is a kind of a very, very demanding and difficult situation. So our concept is when we move into the space, you need to bring together your basic environmental environment, right, together with you. So we call it core biome. It's a food production and also the closure ecosystem and material cycle. Okay, let's simplify it to the now, right? And what is core technology? Core technology is, I heard the term core technology from the different company because it's a term becoming kind of popular. But what we define core technology is two different things. Because if you go to space, what is the most difficult things? It's a low gravity and space radiation. Right? Of course, before discussing that, the space environment, you have to support the lifeline support. And that will be proposed by Dr. Sakurai from JAXA. He will talking about, after my talk, about ECRUS. It's the most important essential concept for supporting the life. But if we think about moving into the different planet, you have to overcome two different things. It's a gravity and radiation. Right? Because if you only stay in the short term, that the gravitational force is not so serious. And also the space radiation, those will not reach a serious level. So if you only stay in the longer time, like more than 1 year or generation, then you have to think about gravity and protection. And then you can build a society, but society should be based on what you have, how many food, how much food you can supply, how much water you can supply. So the society should be minimum and effective. So it should be a kind of a different form, like a society that we have in the Earth. We do not need to intentionally build a society because a society in the Earth is established by itself, because lifeline infrastructure in the Earth is almost secured by the based on the natural resources. Okay, it's a different picture with including the simplified picture. Ocean, forest, soil can be natural resources, but if you move to the different planet, let's summarize those ecosystems. And technology could be artificial gravity, and society is there. So what is the difference between the past concept? Fundamental difference. The past concept, conventional concept, will be first secure the human centered for the survival, basis for survival in the space. So you have to secure human survival. So the lifeline supporting system is essentially important. And then we will think about, let's provide the water, fresh water. So then you have to have a purifying system of the water, and food is a spatial agriculture. And that is a current concept, I think, for the space development. But we have to move. We are proposing in the three core concepts. We believe that human cannot settle in the space alone. So which means here, so the establishment of the basis of human existence, establishment of the basis for the survival of the Earth ecosystem on other planet. And that is a kind of a difficult thing. And transferring ecosystems that support humans. Is it possible and feasible? And for the transfer ecosystem, there could be a transfer of the seawater instead of fresh water. Okay. And then it's an ideal thing. The ideal state can be transfer the Earth's natural capital, core bio, on which humans should be based on other planet, together with life-supporting resources, and stabilize the existence of Earth's natural capital in other planet. So this is a kind of a picture which is representing our biome in the different environment in the Earth. You can see the earth, ocean, and forest, and seaweed, and hyposphere, and these kind of things. But if you select this, you cannot bring the ocean itself into the different planet because it's so huge. So you could have a very small portion of the ocean, and then select like a coral reef would be nice place, and the forest would be nice place. Those kind of place would be nice. And so to secure, we have proposed like a space forestry and space ocean. What is space ocean? We will discuss today in the very detail. And also, of course, there is a space agriculture, aquaculture, will be discussed with Dr. Endo before, right? And also the space habitation. This was discussed before, but today in the outreach session, Mr. Ono will talking about this, right? And then you have a medicine, space medicine as a core society, and core technology. You have to have a right supporting system and medicine. And then let's come back. What is a space forestry? The space forestry is in the restricted area and to make a plant. However, for example, if you are having in the Earth, for example, I'm introducing the Yakushima Island, which is very famous for cedar trees, right? So it's a natural forest, and in Japan there are so many natural environment, but that Yakushima cedar, and they are supported by the precipitation. It's a giant cedar trees. It's a famous Yakusugi. But the Yakusugi's presence is almost perfectly supported by a lot of rainfall there. So can we build like a Yakusugi in the space? It will be difficult because it requires very long-term stable precipitation. And can we artificially create a rainfall? It might be difficult. So we have to adapt that fit the space, a limited environmental control, right? So Of course, we can enjoy the Earth's natural ecosystem, but we have to thankful the rain and water, right? Okay. And then the space ocean, that is a focal discussion today. So this is a introduction of the Yonaguni diving, right? So actually, it's a hammerhead shark was we have visited, and then the so can you enjoy here? It's a Yonaguni Island, and then there it's a diving, right? And then there is a hammerhead shark is there. But it's important thing is it's very wide, right? So it's a vast ocean. It's a blue, and there is a species. But can you reproduce that kind of environment? I think it's difficult. It's gonna be very difficult because it's a huge. And then the water is good for sea-based animals or fish and also the shark. But for human, we don't need this actually because we cannot live there. But of course, how can you validate the presence of the ocean? Of course, in the Earth, it's free, right? It's already there. But can you pay $100 million to bring this ocean to the space or more? It will cost more, a billion or trillion dollars. So it's gonna be a very difficult and very expensive to realize the migration of this space into the space. So it's just a simplified introduction of what is the role of the ocean in the space migration, right? So if you discuss about ocean in the space, we're gonna discuss mainly in the 4 different things. One is the internal ocean. So internal ocean is discussed many times, and also the surface liquid, and also the ancient ocean, and then the habitable exoplanet, right? So the internal ocean presence in the Europa and Enceladus and Callisto, it's a Jovian and Saturn satellite. Those satellites is located outside of the snow line, right? Snow line, inside of the snow line, most of the planet the water has already evaporated. Exceptionally, Earth, we have ocean because we have a sealed cold trap of the water, thanks to the presence of the troposphere and tropopause, and also the stratosphere. But the other planet is almost dry because they have already lost the water. But those the satellite, which is located outside of the snow line, they have ocean internally. And also the different planets like Mars. Mars used to have an ancient ocean, right? And there is erosion can be seen in the Amazonas. And this is right from the Vladimir Ayropedian from NASA Goddard. And he is saying that in the Martian period, in the Noachian period and the Hesperian period, they should be having an ocean, and there is atmosphere pressure with more than 0.5 bar, right? And they should be protected by the magnetosphere. And it lost after the cool down of the core. And then there is a talk that Venus also has an ancient ocean, like 1 billion years from now, right? We don't know. So if you have a Venusian ocean, then let's go there because it's a hot ocean environment, but it should be because the planet size is almost same. And also there is a habitable exoplanet. Have you ever heard about exoplanet? Exoplanet is located in the outside of our solar system in the sky. Most of the star in the sky has planet, probably. And we have already discovered more than 5,000 planets confirmed. But most of them are not habitable because it is located inside of the recent Venus, which means it's more hotter than the Venus. But if you classify according to the COPARAP, we have 208 planets, which is located in the habitable zone. So inside of the 208 planet, which can be potentially habitable, we have around 50 planets, which is the size of the Earth, which might have hold of water like Earth. We don't know. But we hope at least 50 ocean-like planet is existing in the Earth. No, not in the Earth, in the different planet. So mainly when we talk about ocean, we will discuss these four elements. So now we are discussing about the ocean. But when we think about terraforming, we need a water for terraforming, right? But let's think about ocean, right? If we think migrating, bringing the ocean to the different planet, it will be incredibly difficult. But where we can think about bringing, there is a coastal zone and also the pelagic zone. However, the pelagic zone and the ocean will be very orgotrophic and a wide variety of large marine organisms. And it's a very difficult to bring because it's a vast space. But in the coastal zone, you have biodiversity and coral reef and seagrass bed are the only production. So probably it will be easier in space. The formation of coastal area is necessary, could be necessary because of the production. And then if you think about the full planet covered with the ocean, will be very, very difficult because you have to have an atmospheric pressure more than 0.3 bar, and it is not possible, right? And then it will be very difficult to generate planet-wide ocean for the different planets. However, let's think that if we limit in the partial ocean, could be possible. But if you have a sealed environment, what kind of environment we should bring? And that is a very big discussion, right? So this is a different ocean, which is actually coral reef in the Iriomote Island. It's a UNESCO heritage. So in the Iriomote and Ishigaki Island in the Japan, it's one of the most rich environment in the coral reef, and many, many different types of fish. These are the, and then the biodiversity there is supported by the coral reef. Actually, coral reef is producing oxygen and producing primary production from there. And many different small fish are there. So in terms of the supporting the biodiversity, the coral reef is very good. However, please think, if you want to have a fish to the food for us, it will be difficult because there are only small fish and very different fish. And of course, we can eat a kind of a glucon heater, like, but it's difficult to eat those fish. So the environmental purpose and also the human purpose is somehow different, right? So this is a very important discussion today. We want to raise this discussion with Professor Masuda and Professor Endo. If the marine ecosystem is to be determined, what are the output? Can we make a design edited by the aquaculture or aim to maintain the different ecosystem as possible? Or what is the purpose? You want to have a aquaculture, you want to have a like ocean, other biodiversity. If we can have a big ocean, we can stabilize the climate. However, it's a very difficult to think about covering full ocean into the lunar surface. However, even for the limited area, the ocean or water play a very important role for stabilizing the temperature and stabilizing climate. So the core biome concept is like using this small place and then to try to organize something. So let me move on the different aspect in the surface of the Earth. So in the surface of the Earth, if you think about ecosystem, you have aerobic condition and anaerobic biome. So aerobic biome is supported by the plant, which induce the photosynthesis and also the cultivation of the animals. But the anaerobic biome, it's like under the ground. It's reduction and methane production, right? So it's a completely different, but it exists at the same time, right? So that when we think about bringing the ecosystem, there are many issues because, for example, how can we select the species, right? And if you bring like a pet, you have puppies, you have a dog and a cat, you probably want to bring them. However, they need oxygen, they need food. How can we live with them, right? So this is the biggest one. But if you think about like insect, do you want to have insect in the space? Yeah, many young people don't like insect now. I like insect, but how about cockroach? So if you have many cockroach in the space, I don't know if you like them or not, but it's a big discussion, debate. And also, if you are forgetting about animals and insects, there is a big issue whether the ecosystem is aerobic or anaerobic environment. Because to sustain the ecosystem as aerobic, you have to supply oxygen, you have to secure the photosynthesis. It's a very difficult way. So this is just a demonstration of what we are doing. It's a kind of a detection of the species by artificial intelligence of the like. This is a purpose for maintaining the small ecosystem and then supporting like species, right? But this is just okay. The next is introduction of the biosphere 2. So we're gonna have a talk with from John Adams after my talk, but he will give a talk with the video. But we have experience in this environment. This is a biosphere 2. It's a world famous artificial natural ecosystem in the world. You have an ocean. You have like a wide variety of species here, and also this is about technology, core technology, and we will discuss ECLUS by the Professor Dr. Sakurai. And then the natural resource utilization and protection of the space radiation and core bio. I don't get into the detail, but this is a transporting system in the space for the securing the artificial gravity in the moving to the different planet, right? So when you move to the different planet, it will be nice to have like artificial gravity. This is a concept that we have developed. It's a hexatrack concept and moving to the Mars, right? So, but transport to the Mars will require 6 months, and it is better to support it by the centrifugal artificial gravity. Okay, so the different final topic is a terraforming. If you think about the terraforming, is the ultimate means of the transferring Earth ecosystem to other planet. However, please think seriously. It will be difficult. Gravitational force cannot be reproduced. And atmospheric dissipation cannot be stopped because the atmosphere or the Mars is always losing. And then that will request a very big difficulty. So if we have a chance to bring the atmosphere to the Mars, probably those atmosphere cannot be stayed because of the lacking of the magnetosphere and protection, and insufficient absolute amount of necessary element, hydrogen, nitrogen, and carbon. Why hydrogen is important? Because the lack of water. For example, if you go to the moon, you have a lot of oxygen. However, you don't have hydrogen, so you don't have water, sufficient water. So you have to bring those materials from the different planets. So instead of having terraforming, we are proposing terra window. What is terra window? Is like a closure environment initiating Earth system, right? And then in this discussion, we have to secure the oxygen level and biodiversity control, and material circulation control, boundary control, energy control, gravity. So oxygen level control, you have to have, of course, forced oxygen generation by electrolysis, or you have to secure biological oxygen production. And biodiversity control, that will be a most difficult thing because you have a very closed system, and how to maintain the number of species and in the density area, you should treat by artificial intervention. And material circulation control is also very important, but you have to have a closure ecosystem and watch the monitor those materials. And boundary control is temperature control, and energy control is important, and also gravity is very important. But we don't know whether we will need a gravity with 100% of the Earth, or you can have a lower gravity in the space. Okay, so this is the end of my talk, and thank you very much. Thank you very much. So, okay, so initial, the session, we will start the core bio session with the break, but is it okay that we can restart? And the first talk will be from John Adams. So the John Adams is a deputy director of the Biosphere 2. He will give a talk through video, and then please, can you, should I, sorry, I have to share the screen with sound, then you can think. Okay, so.
Hello, everyone. My name is John Adams. I'm Deputy Director and Chief Operating Officer here at Biosphere 2. And what I'd like to do is to give you a bit of an overview of Biosphere 2, sort of its original origins, the research significance of it, and some of the significant research outcomes for Biosphere 2. So I'll go ahead and start by sharing my screen. And, you know, when we think about Biosphere 2, it's really not only about the facility, but its primary focus was Biosphere 1, the Earth, but also there were a lot of implications about Biosphere 2 and what it would mean from a perspective of how could this facility improve our ability or survivability on the Moon or Mars. You know, when we look at Earth, Biosphere 1, there's only one of them. No matter how deep we look into space, how many exoplanets we find, all of them will require significant protective gear and life support in order for us to be able to survive on that. Earth is the only one where we do not need that. And so much like the emphasis that is being put on today of what it's going to take to get back to the Moon, to actually get to Mars, and more than just getting back there, I have no doubts that we can put boots on both of these. But what's it going to take to actually set up a colony there for an extended period of time, or some type of permanent colony? I think this is sort of a perfect perspective. You know, we're here on Earth and we're looking to Mars or the Moon to go. And those very similar aspirations were very prominent, you know, beginning in the early 80s up until the late 80s or early 90s, when a group of people were able to convince an individual that he should fund a project that would allow them to better understand Earth systems. Yes, it did have a business purpose, and a part of that purpose was not only understanding Earth systems, but could they develop intellectual properties and patents that would allow us to more successfully colonize the Moon and Mars. So they built Biosphere 2. If you haven't been there, you've got to come, but Biosphere 2 is located just north of Tucson. It's about 50 minutes from main campus at the base of the Santa Catalina Mountains. And so Biosphere 2 is a closed system, and we've been thinking about closed systems from very sophisticated ones like Biosphere 2 to the one that Claire Folsom is holding here, where you seal up a bottle, you've got a little bit of algae, maybe some invertebrates living inside of it, and it's a closed system. It doesn't need any input from the outside, to more basic ones like many of us have in our homes, some type of a terrarium like that one that you see here in the image as well. Now, people have been doing these types of things for a really long time. The images that you see here are historical images from a Russian experiment called BIOS 1, 2, and 3. This was in the early 70s. And this is a facility that is significantly smaller. I mean, on the order of about 1,000 to 1,100 square feet. You had people living inside for extended periods of time, growing all of their own food and using those biological processes in part to balance the atmosphere inside of that facility to support extended stays. Now, more recently, you've got experiments like that that's happening in Beijing, China. They call the Chinese Lunar Palace. I think it was about 2 or 3 years ago now. They were able to stay inside this facility, grow all of their own food, stay for extended periods of time. And they were able to stay inside for just over a year. I think it was like 370 days or something thereabouts. But again, this is a significantly smaller facility than that of Biosphere 2. I mean, something on the order of about 1,600 to 1,700 square feet. So a modest-sized home. Now, back in the late 80s, early 90s, again, this group had the aspirations of building the largest hermetically sealed facility to better understand Earth systems. And inside this facility, they were going to enclose, encase different biological systems in the hope that they would be able to leverage those biological systems to support the needs of the humans. So this is an early construction photo. When Biosphere 2 was completely buttoned up and sealed, you can see the concrete that's going down over here on this one wall. What you can't see is the entire facility. Everything that's under glass is lined with stainless steel. It's a 500-ton welded stainless steel liner. That was to ensure that there was no interaction with the surrounding desert soil. The overhead structure was put together with these cross members, these steel cross members that have fins on them. They referred to as a space frame. It was constructed and designed by a company called Pierce Structures out of California. And it's these interlocking members that allow them to have a relatively open overhead space to allow for optimal light transmission. Because remember, inside of here, these biological systems they were going to grow were prominently dominated by plants, and those plants are going to need to photosynthesize. And one of the reasons you build a facility like that here in southern Arizona is because in southern Arizona specifically, and in Arizona, we're one of the sunniest places in the world. We get over 300 sunny days a year. You want to optimize that light transition, take advantage of all those sunny days so you can grow those plants and you're not having to supplementally light them. Because we know anytime that you begin to supplementally light them, even with the advancements of LEDs, it becomes very, very costly from an energy consumption standpoint. And you a lot of times generate a tremendous amount of heat. So inside Biosphere 2, they incorporated and added in a tropical rainforest. This, for the most part, model the region that you found down in South America, a subtropical savanna and thorn scrub, an actual ocean system that modeled the Caribbean reef environment. This is about 1 million gallons. It has a reef was stocked with hard coral, soft coral, sea anemones, sea squirt, urchins, algae, fish. Right behind it, you see this notation, marsh. This is actually a mangrove system where we have red, black, and white mangroves. They actually went down to the Gulf Coast of Florida. There was a site slated for development. They were able to collect those trees that were going to be moved or removed for this development, put them into large containers and ship them across the country. And this included not only the root ball, but the soil, the water, as many microorganisms that came along, and even some larger macroorganisms, and then transplanted them into here, the Biosphere 2 mangrove system. On the far end of the mangrove, or on the far end of Biosphere 2 is a desert. This is really a coastal fog desert. So if you were to travel from Tucson and start to work your way down into Mexico, over to Baja California, and then down, you're going to encounter an area, in particular when you get on the west coast of Baja California, that's known as the coastal fog desert. So most continents have a fog desert. This is typically found on the western edge. And here, because of that proximity to that coast, those temperature differentials, you get this fog that rolls in, even though you don't get much precipitation in traditional forms. Plants have specially adapted to be able to take advantage of that moisture in the air. when the facility was originally built, they set aside of the whole facility is a little over 3 acres. A half acre was set aside for this intensive agricultural biome. This is where they grew crops in a very traditional means in soil. They didn't have hydroponics or some of these other more advanced ways of growing crops that we think of today. They had a space where they lived. So they had their apartments, they had their kitchen, their dining area, their medical office, their restrooms, their machine shop, a workout area. They even had a place in this human habitat where they had some farm animals. They had some goats, some chickens, some pigs to supplement their needs when they were inside. And then you see this facility called the lung. There were 2 of these. You can see one in this picture, and these were vitally important. When Biosphere 2 was sealed, it only lost 10% of its volume annually. The entire volume of the structure is 7.2 million cubic feet. It lost 10% of that annually. And all of you know that when you have a fixed volume and you add temperature to that fixed volume, especially for air, you're going to see an expansion. As it expands, because that volume is fixed, that means you're going to increase pressure. If you don't do anything to compensate for that pressure, there is situations where you can compromise the integrity of the structure. You can blow it up. And the engineers who designed Biosphere 2 knew immediately that was something that they had to compensate. And so the lung is really a variable volume air chamber. It has a large diaphragm in the center. It is connected through underground tunnels. And as the air expands, it goes in there, that diaphragm lifts up, increasing the volume. And contraction ensures that you take up that additional pressure, but because you always have essentially a counterweight, this weight sitting on the air mass, the overall pressure inside the facility never changes. So therefore, those leaks that you do have are always constant, and it only lost 10% annually. This is, this rivals in some situations the leak of the International Space Station, and is typically 1,000 times more well sealed than your a typical skyscraper. So pretty remarkable from an engineering perspective what they were able to achieve. Now, the objective was to seal 8 people inside and have them stay inside for 2 years. So you see, this is a historical image of that first crew going in September of 1991. They stayed inside for 2 years. Most of their activities and time, even though they had aspirations of doing all of this science, was focused on the farm. How could they get at intensive agricultural biome to produce the amount of crops they were going to need? And it was a struggle. It was really where all of their time efforts were primarily put, because although nutritionally they were okay, they were always calorie deficient. And so they were always struggling. Some of it was because it was an El Nino year. We had lots of cloud covers. Others where they had some challenges with some traditional crop pests. And finally, the folks that you see in here were just not very good farmers. And it is an art to be able to get things to grow. Now, when they sealed the door, when those 8 people went in, this is what happened. Almost immediately, you started to see oxygen going down, and it dropped all the way down to 14.2%. And so this was at about day 500 into that 2-year mission. And so immediately there was a recognition that when it got this low, they needed to do something. They needed to add oxygen back into the system in order for the safety and well-being of those 8 people who were sealed inside. Now, what they didn't do is they didn't disclose this to everyone, okay? So they tried to hide that. They were so concerned with their reputation, their image, and so they didn't even tell the person who was handling their press relations. But in the cover of darkness, they had a large truck, an oxygen truck, come in. They pumped oxygen into one of those lung areas. It was a great relief for the people living inside. They were dancing, they were running around because they felt reinvigorated because of all of this. But one of the other things is when they got past all of this and they were able to successfully stay inside for those 2 years and come out, and they started to look at the data and figure out, okay, this is a sealed structure. We know what our leak is. We pretty much know what the biological systems are doing. But where is the additional CO2 going? Because a really well-known, a world-famous geochemist and a graduate student of his, this guy was by the name of Wally Broker. The graduate student of his at the time was a gentleman by the name of Jeff Severinghaus. And they started to mass balance their equations, and they couldn't get them to mass balance. Again, they knew what the soil was doing. The soil was giving off tremendous amounts of respiration. That farm area and that intensive and that rainforest area, they put really rich soils to support the intensive growth of plants. But what they anticipate is that those microbes were going to be so dominant that consumption by the microbes of oxygen, that release, that respiration of CO2 outpaced the ability for plants to photosynthesize, hence why you see this decrease. And they knew what all those numbers were, but again, they couldn't figure out what was happening. And the equation up on top is the additional thing that was happening. There's massive amounts of concrete that went into the infrastructure of Biosphere 2. And so as that concrete was curing, this calcium hydroxide was combining or reacting with CO2 to become calcium carbonate and a little bit of water. And so this is where those additional carbon and oxygen molecules were being bound. And so there were researchers who were able to put this together, who were able to mass balance it. And they said, you know what? This is an incredible facility to trace geochemical cycles and not those. And it's not as well suited, in their opinion, for people living inside and dealing with all the drama that comes along with that. Because not only could the people not breathe when they were inside, that's why it got down to 14.2%. They were always hungry. And they couldn't get along. These social and psychological challenges that are so well documented in many different studies, whether it's done by NASA or other space agencies, played out. Even though the facility was large, they hoped that that would mitigate it. It was not enough to offset the onset of those. And so there began a transition to move away from people living inside and use it as a large Earth and environmental science laboratory. And today, I really like to think of Biosphere 2 in a similar context to the Large Hadron Collider or the Giant Magellan Telescope. So physicists have these colliders, we smash atoms together. What are those fundamental building blocks? You know, astronomers, some of the most famous and successful astronomers are right here at the University of Arizona. The ability to build these really giant, sophisticated mirrors happens right there at the University of Arizona Stadium underneath of it. And we put them in large arrays on remote mountaintops into space to look to the ends of the universe. But we've never created an equivalent tool, in my opinion, to understand Earth systems. And Biosphere 2 is that tool. It allows us to tease apart some of these fundamental interactions, some of these fundamental feedbacks, to look at how these systems respond. And, you know, essentially Biosphere 2 is that magnifying glass into these biological systems, whether it's in the rainforest, in the ocean. This former agricultural space has been converted into the Landscape Evolution Observatory by the University of Arizona and has been in place now for nearly 8 years. Now, Biosphere 2 is this middle ground. Okay, so on campus, at universities and labs around the world, we have these very precisely controlled, very sophisticated boxes, maybe the size of a refrigerator, a little bit bigger, where we can grow plants very precisely control the light, the temperature, the humidity. We even see these types of things in shipping containers now, maybe not quite as tight a control, but nonetheless, these are mesocosms. They're much smaller. Then if you jump to the outside, we have these large observatory programs where we can measure partly what is happening in landscapes, whether it's a watershed, it's a conifer forest, a boreal forest. In this particular picture, you see an Amazonian rainforest, but we can look at what's happening in those systems. But we need this middle ground, and that's precisely where Biosphere 2 falls. It's this intermediate step that allows us to partially scale from what we can precisely measure in the lab to what we can observe in the field. And again, the field has all of the natural biological diversity, but has very little control. The mesocosm has tremendous amounts of control, but lacks that biological diversity. And again, Biosphere 2 has lots of complexities and controls, although it's not a perfect, it's not an analog. It allows us to partly control some of those variables in ways that we just can't do, but achieve a scale. And that's what's exciting. And that's the challenge in a lot of these sciences, is how do we scale from small to large? Now, what are we doing today inside Biosphere 2? The picture on the left is we're addressing water scarcity. We're looking at the fate of water in semi-arid environments. We're looking at how tropical rainforest systems respond to things like drought, increases in temperature, and increases in carbon dioxide. Our ocean system, not only are we looking at ocean warming, but some of the most famous studies in Biosphere 2's oceans focus on the impact of increasing atmospheric CO2. And we have faculty that are looking at how you combine renewable energy with the growing of agricultural crops to create and optimize a system that actually benefits not only the crop, but the production of energy. So the Landscape Evolution Observatory is the University of Arizona's institutional experiment at Biosphere 2. They completely renovated that farm area, they removed all that, and they built what you see in front of you. This is one of is a volcano out of Biosphere 2 came out of the ocean. We manipulated the carbonate chemistry. This is when CO2 goes up in the atmosphere, it dissolves into the water. And what happens here is CO2 plus H2O becomes carbonic acid. Okay, carbonic acid drives the world's ocean's pH down. So we hear about that today as ocean acidification. But what also happens is that carbonic acid reacts with carbonate that's readily available. This carbonate ion then is reacted with this carbonic acid, becomes bicarbonate. This bicarbonate is no longer in a form that's readily uptakeable for corals, and so corals suffer. And especially when you see an increase in atmospheric CO2 like we've seen, and values as we have today, you see a significant reduction in calcification rates directly attributed to the reduced carbonate ion availability.
Okay, actually,
and so today, we also see massive bleaching events on reefs around the world. Great Barrier Reef has lost 50%. One of our collaborators who was on our board of directors, unfortunately, she lost her battle with cancer, Ruth Gates.
Especially for this coral reef, because the coral reef is dead once and then they are trying to recover. The thing is, this is a very big struggle, but I will skip because of the time constraint of the session. But thank you very much, Anna, for the, he's not present, I'm sorry. Okay, so the next speaker will be Dr. Masato Reiji Masuda. Reiji Masuda, Kyoto University, and he's a director of the Maizu Fishery Research Institute, right? And also the Field Research and Education Center of the Kyoto University. He will talk about the space ocean, but based on his experience, is observing constantly in the ocean environment. Okay, so Professor Masuda, can you use this microphone? Oh, if it's working.
Yes, I think so. Is it working? Okay, thank you. Can you? Okay, thank you, Yamashiki Sensei, and good morning, everyone. And I'm Reiji Matsuda, and my talk is titled Ocean, Environment, and Space. To be honest, I know nothing about the space and nothing about the moon. I've never even been there, so sorry to tell. But the place I frequently go is underwater, and I'll talk a bit about my experience in underwater. And I consistently dive in three different places, so I talk about that. And before about that, I want to generalize some characteristics of major aspects of the ocean. Ocean has strong environmental stability. Temperature change is less compared to terrestrial system. And it also has a high turnover rate. Compared to cedar trees in Yakushima Island, it took 1,000 years to grow. Phytoplankton in the ocean takes only a few days to grow. And the third point is high resilience. Many ancient animals or plants survived only in the ocean, but not in terrestrial system. And it's relatively strong to impact from outside. Then it does have protection from the ultraviolet radiation. So there may be something we can learn from the ocean. So let me talk about my visual sensors. I conduct visual sensors in 3 different places, and the most frequently dived place is just in front of my research station. The goal of my research was to list which species of fish are there, and then track both seasonal change and interannual change. To do this, twice a month visual census was started in January 2002, so 22 years ago. And for this 200-meter line transects are set triplicate, and I record every fish species with size and abundance. And to record fish in underwater, I use underwater slate. So record fish name with a pencil. It's super analog. And a typical fish I would encounter is black sea bream or kurodai. And do you know why black sea bream is black? Well, many sea bream species are red, like madai is red, while this species live in very shallow water. So they have to protect from UV. So they tend to, shallow water sea breams tend to have black color. And recently, this species is increasing. In following graphs, x-axis is year of observation, and y-axis represent total number of each species I encountered in each year. Obviously, black sea bream is increasing, and it's resident fish, so I can find them whole year round and also omnivore, so they can eat both animals and plants and many different things. And so they are increasing. And another species, Mejina or blackfish, is also increasing. This is herbivore. So they eat seaweed. And they're actually very tasty fish, both with sashimi and also carpaccio. I love cooking, so I often grill this fish. And I would recommend to bring to the space this kind of fish is more suitable compared to tuna, because if you want to grow tuna, you need some fish as their diet. While for this blackfish or black sea bream, they can grow with vegetable, seaweed, so that it's more better. It does have better cost performance. Then the gobies, they're also increasing, but and also another species of goby, Kutsuhase, is increasing. Apparently, they are too small to bring to eat, so not suitable to bring to the ocean, to the space. And not every fish species are increasing. Actually, ainame, greenling, is decreasing. Some species are increasing because they are more adapted to warm water, while ainame or greenling is cold water species, so they are decreasing in the Sea of Japan. And so sujihase, they are not necessarily cold water species, but they are losing competition against warm water species. Then this is seahorse. Again, this is decreasing. The reason they are decreasing is because they are losing their habitat, which is seaweed. Because there are many herbivores that increased with a warming trend, seagrass, seaweed habitat decreasing, so that they have lost their habitat. Their typical rabbitfish is a typical herbivore, and they eat lots of seaweed. And after the recruitment of rabbitfish, we lose the algal forest. This is the summary of the my underwater visual sensors in our area. X-axis is date of the diving, and the uppermost graph is water temperature, and it's the highest is 30 in the surface, and in winter it goes 5 or less in surface, and bottom at the bottom it's about 10 degrees. And both number of species and number of individuals are high in summer and low in winter. So it looks very consistent. But if you look at the water temperature carefully, actually it's gradually increasing. The lowest bottom temperature is non-significantly increasing, but average bottom temperature is significantly increasing with a pace of 0.05 degree per year, or 1 degree in 20 years. I thought that it's too rapid, but actually, according to the data in the Japan Meteorological Agency, it's the water temperature in the Sea of Japan is increasing with this pace. So 1 degree in the last 20 years. Then is the warm water species really increasing? To test this, I defined center of distribution in Northern Hemisphere. What's that? Each species has a limited area of distribution. For example, yellowtail found from Tokara Island, or 30 degrees north, and to Hokkaido, which is 45 degrees north. So taking the average of those southern and northern limit, I would say I can say that center of distribution is in yellowtail or woody would be 37.5. While this tropical species, Kurohoshi fuedai, or black spotted snapper, can be found in the equator and the middle central Japan. So this southern species does have a lower value of center of distribution. Then I plotted the average of all the fish found in each year, center of distribution in each year, and it's apparently decreasing. So for the last 22 years, the number of warmer water species is increasing. As further analyze what's the feeding habitat of increasing and decreasing fish, then herbivore or those eating algae are increasing, while benthivore that are eating like crustaceans are decreasing. Another place I'm diving is near the nuclear power station. There's a Takahama nuclear power plant located about 15 kilometers from our research station. So I'm doing monitoring because they provide warm water discharge. So this may be inducing some environmental change. And they built another power plant which is run by coal-fired, and it also provides thermal discharge, but less amount. So I dive 4 times every winter. In mid-February, which is mid-winter, I found Sorasuzumedai, or blue damsel fish, which is tropical, and there are quite many. And also cut ribbon wrasse. This species is a tropical species, and they replaced common wrasse, which is typical in temperate waters. Then they suspended the operation of the nuclear power plant. Then warmer water species started to die. And so tropical sea urchin, diadema or gangaze, died out. Then temperate species returned very soon after this collapse. And so seaweed and temperate fish. This observation can be summarized as follows. Winter temperature is quite consistent in 2 locations, Maizuru and Sezaki, while in Otomi, where nuclear power plant was located, the water temperature was 2 degrees higher when it's in operation, while it dropped down. With this change, fish species decrease, and center of distribution, which is the representative of warm water species, dramatically change. The third place I'm diving is Kesennuma, and you may remember that they had suffered a large earthquake and tsunami in March 2011. And I started diving 2 months after that. And ever since I dive every 2 months. And last time I dived was 76th. Every time I go there, I dive 4 locations in Kesennuma and do underwater observation. Well, in 2 months after tsunami, there are many dead fish in sea bottom. In 6 months after the tsunami, there are many gobies. This is because they do not have predators at that time. Then gradually, larger fish returned, such as surf perch and black rockfish. Then even larger species like sculpin and large blenny return. So these are predators. So x-axis again is month after the tsunami, and water temperature is high, 24 in highest, and in sometime 2 degrees, very cold in winter. And let's see, number of individuals returned in the first year because there are many gobies. But at that time, there are fewer species. In the 2 or 3 years, fish species returned. If you look at species composition, you can see that the smaller species returned first, then followed by larger species. I also observed invertebrates. Then I found that jellyfish returned within the year. Then sea cucumber took 3 years, and abalone took 5 years to return. And this is exactly correspond with the lifespan. Jellyfish can get matured in 6 months, while it takes 3 years and 5 years for sea cucumber and abalone to get matured. So the recovery time depends on the lifespan. The last topic would be which fish should be brought to the moon. Well, sensible answer would be first try some freshwater species like carp. Carp is actually the most commonly aquaculture species in the planet. I mean, in Asian countries, they produce carp and also catfish. And catfish is actually quite tasty. We sometimes try in our barbecue. And it actually tastes like unagi. If you really stick to marine species, then I would recommend black sea bream. They grow quite fast, and they can live both in marine water and survive in fresh water, and tasty. And okay, that's all for my talk, and thank you for your kind attention.
Thank you very much. Very good recommendation that John was looking for, right? So you so okay. So one question, if you want to have, if anybody address this talk, if there are somebody who is wanting to ask something, yeah, no, not you, not you. Yeah, no, you want to say something? No. Yeah, one question.
So in particular, with regard to the freshwater species, are there any studies or any examination of sort of the integration of the freshwater species and the land environment, the species or the plants and so on the nearby shore? Because it seems to me for the space application, you cannot you won't have the water by itself. just like you don't have the on the Earth, you don't have the water by itself. There's the shore as well, and there's runoff. There's many minerals and many debris come from the runoff from the land, and they provide nutrients and in the water, in the lakes and so on. So I'm just curious if anybody has looked at that or any consideration of the combination of the land and the water.
Okay, the combination of land and water, which for fresh one, well, perhaps it's more related to the Professor Endo before, but that experiment we. Specifically for rearing fish in water, in freshwater fish, basically we provide prey and oxygen, and not specifically any extra mineral or such. So either in freshwater or marine system, and so for in closed system, the only basically it's they can grow just by diet and oxygen without like minor mineral. But for longer term, like growing plants and others, as an ecosystem, apparently you need some minerals and so on. And you can hear more about culturing fish from Professor Endo's talk, following my talk. So, thank you.
Okay, thank you. Thank you for Professor Masuda. Very nice talk. Okay, the next speaker will be what John looking for. He's talking about the space aquaculture, which really producing a good sashimi in the lunar surface or different environment. But he's a really expertise and finding most appropriate species in the space for really for the food purpose and feeding purpose, and also the type of the fish. And also he has also experimented in the long gravity and experiment. So he will talk about this. Okay, thank you, Professor Endo.
Okay, good morning, ladies and gentlemen. And thank you for your kind introduction, Yamashiki-sensei. My name is Masato Endo from Tokyo University of Marine Science and Technology. Today, I would like to talk about aquaculture in space. This is today's content. First, I talk about background. Next, development of aquaculture technology with material recycling and artificial food chain. And the third section, behavioral analysis of farmed fish under different gravity conditions. And finally, I would like to summarize these contents. What's the background? Food production is an essential consideration when humans consider permanent space habitation. We have been conducting research with AIM to introduce aquaculture to food production subsystem of human habitat in space that will be constructed in the future. Food production in space habitat needs establish of biological production system considering material cycle, and I think it will be necessary to think further ahead. Looking further ahead, we believe that maintaining dietary diversity will be important, especially when considering the production of animal protein. It is necessary to search for species that can adapt to the space environment. This requires survival, breeding, growth, maturation, and reproduction. It is considered desirable to use fish that have been used since the early days of human exploration, human space explanation and development. From these prospects, we have been considering research using the edible fish, tilapia. Yeah. Research can be broadly divided into two categories. One is about establishment of aquaculture system with material recycling. And the other is about appropriate judgment of fish to space environment. So I'll start by explaining development of aquaculture technology with material recycling and artificial food chain. We first conducted research with the aim of establishing a seed production system with material recycling. We use waste discharged from tilapia culture with recycling aquaculture system for production of chlorella as a fertilizer. As a next step, culture of water-free Moina macrocopa fed on the chlorella. And finally, we fed Moina macrocopa to tilapia juveniles. This is biomass conversion by artificial multi-step food chain. If this challenge is successful, it will demonstrate that it is possible to produce fish from fish waste. I won't go into detail, but the results showed that about 5% of the nitrogen and phosphorus excreted by fish was accumulated in young fish in one cycle. Although this efficiency is not high, we believe that efficiency can be increased by recycling materials many times. Aquaponics is a combination of the recycling aquaculture system and a hydroponic system. Fish excretions are used as fertilizer to grow vegetables hydroponically. Substances excreted in the breeding water are removed to maintain water quality for a long period. time by cultivation of the plants, vegetables. It has reached industrialization on the ground and is attracting attention as a food production that does not emit pollutions into the environment in the future. And also, I think this combined food production system can be applied to food production in space. Next, I would like to explain behavioral analysis of farmed fish under different gravity conditions. We carried young tilapia fish on board an aircraft and observed their swimming behavior under different gravity conditions, including microgravity. We conduct an experiment in which we fed water-free food under microgravity. I'll show you the video. In visible light, they turn their back to the light here. Right? And they ate the water-free. In visible light. But in infrared light, they are around and were unable to eat them. This is water-free, but they cannot eat. So next, to investigate adaptation to various low gravity environment, tilapia juvenile were placed on an aircraft and their swimming behavior was observed. The gravity environments of 0.1 and 0.2 D are obtained by maintaining less parabolic trajectory. As a result, it was found that under microgravity, posture control depends on light. And most individuals swimming normal under 0.2 D. And the boundary was 0.1 Z. Okay. Our experiments so far have shown that tilapias survive and feed in low gravity environment, including microgravity. In the future, it is necessary to investigate growth, maturation, and reproduction through long-term rearing. In addition, we performed light-dependent posture control under microgravity and gravity-dependent swimming under 0.2 Z. In particular, it was found that it can swim by sensing the gravity of the moon and Mars. Finally, I will summarize today's content. Our studies so far has revealed the methods of rearing operation of aquatic organisms under different gravity and material flows in aquaculture with waste reuse have been grasped. In the future, from now on, it will be necessary to investigate and study the entire food production subsystem of space human habitat, control technology related to the operation of the total system, understanding of material flow, energy requirements, etc. That's all. Thank you for your kind attention.
Thank you very much. He's the one who discovered the properties of the fish in the space, and also how can we feed them, how can we cultivate them in the appropriate way. So any questions or any suggestion about the question, anything could be okay. But John, you want to say something again? Yeah, please, Mike.
So thank you very much for your very interesting results. You've looked at the fish in the microgravity.
Yes.
Has anyone done any studies looking at fish in 1/6 gravity?
Yeah. So the posture control depends on the light to gravity. That border is 0.1 Z. So they can adapt to 1.6 Z, and they maybe they show the normal swimming on the moon.
In 0.16.
Yes.
Okay. So then they show the normal swimmings, and so they can eat, and so in principle they can reproduce. Yes.
Yeah. But
So
yeah.
But now my real question. You have studied the recycling, and you're looking at the recycling of the waste from the fish into the fish. So one idea for making a large habitat on the moon is fabrication of the habitat from the regolith.
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 Yeah.
So, but if you look at many locations where you have arid farming, they can have arid farming with flooding, and so the minerals in the soil get into the water.
Yeah.
And in many locations where they do this kind of farming, they flood the field to get rid of the salts and dissolved minerals because it's damaging for the plants. So I'm just curious if you have looked at all at how well maybe the fish and aquaculture could remove minerals like salts and metallic elements from the water. I'm thinking about an integrated solution for the moon, where you may have made you don't have a glass tank, you have a tank, you have a pond made out of liner materials from the regolith. So you have to worry about the minerals in the regolith dissolving into the water.
Yes.
Maybe, so maybe the fish and the aquaculture could be one way to process the tank and remove the minerals.
Yes. So
I'm just curious if you've looked at other materials, other minerals, other chemicals other than the fish waste.
yes, yes. We
Long question. I apologize.
okay. We are not only analyze the nitrogen and phosphorus. Some kind of minerals we analyze, and we define utilize the other minerals and other minerals. First, we can cultivate the chlorella from the chemicals, the minerals. So I think the cultivation of chlorella using the mineral from Legoris, I think. So the some kind of minerals utilized for fish culture, I think.
Thank you. Thank you very
Thank
much.
you very much.
Thank you very much. So now let me thanks for Dr. Endo.
Thank you very much.
Okay, so next it's Japan and JAXA is collaborating officially for the Artemis project, and here's a focal point for the ECLUS. It's environmental control life supporting system, which is required especially for the gateway station that we are planning to build in the orbit, Lagrangian point of the lunar surface. And of course, the ECLUS exists International Space Station, but we are formally discussing the expansion of the ECLUS system into the further larger structure, focusing on mainly about the gateway and also other so on. Without ECLUS, we cannot survive because ECLUS, you have to remove the carbon dioxide and secure the level of the oxygen. So he will give a talk about this technology. Thank you, Professor Sakurai.
Thank you very much, Yamashiki-sensei. Today, I would like to talk about the physical-chemical environmental control and life support system ECLUS for manned space exploration. Previous talk is a very exciting aquaculture, but it's a very realistic, not so exciting. But anyway, this is a International Space Station, very big solar panel. And here is a Kibo Japanese module. Next is the ESA Columbus module. Here is the American module, and the next one is the Russian module and the Russian service module. Astronaut can walk inside of here. And inside of here, we have to keep temperature and humidity, air condition, and so on. ECLUS is important. And this is the International Space Station. Here is a Kibo module. Here is a European Columbus module. Here is a American module. And here is a Russian module and the Russian service module. There is some mark. Green dust is a carbon dioxide removal. Carbon dioxide removal machines are here. Russian service module and here, Node 3 module. And
American laboratory module Destiny. And next green one is trace contamination control. It is activated carbon. Astronauts have to training 2 hours every day. And otherwise, astronaut bone or heart is weak and weak. So to keep astronaut health, they training every day. But there's no shower or no water. So the air condition smell level is increasing. So we have to take care in order to remove smell. Activated carbon is necessary. So TCCS, Trace Contamination Control System, is here, Russia module, Node 3, and US laboratory Destiny. And this is the oxygen generation here, here, here. So almost everything, 3 installed inside of the ISS. Because if one machine is out of water, second one is working. If second machine also out of order, third one is working. So we call it two fail-safe system. It is a base of designing of life support system. So we have to almost everything 3. So international station very big. This one is oxygen generation, water electrolysis, and other oxygen generation is a solid fuel oxygen generator. It's made of Russia. This is a KCl04. So if this cartridge heat up to 500 degrees Celsius, oxygen generated. And this is keep the air clean. This is removing of the carbon dioxide, LiOH. This cartridge remove carbon dioxide 1 day per person. One day, one person generate 1 kilogram carbon dioxide. This cartridge remove it. And this is a one-way use. It produce waste every 3 kilogram waste. So this one is a carbon dioxide removal assembly, NASA SHIDRA. This is a regenerative type. And this is a trace contamination gas removal system, TCCS. This is activated carbon. And once upon time, astronaut consume oxygen and discharge carbon dioxide. And carbon dioxide is thrown away to the space. And this is oxygen generation, water electrolysis. Oxygen consume, astronaut consume oxygen, and byproduct hydrogen was thrown away to the space. So if we reuse carbon dioxide and hydrogen, so that idea is a Sabatier reaction. So Sabatier reaction, chemical reaction, 1 molar carbon dioxide and 4 molar hydrogen and heat with catalyst, ruthenium catalyst, 350 degree, produce methane and 2 molar water. So CO2 change to the water. If we obtain water, we can water electrolysis, and we can produce oxygen again. So we can make a recycle system of oxygen. So another one is dehumidification equipment. In the ISS, cooler system working, and cooler system generate concentration water. So we have to remove the water from air. Another ecosystem is water regeneration. This is a toilet, so urine collected in the toilet. And urine treatment, in-air processing urine unit, UPA, urine is heated and distilled to recover water. Non-volatile impurities and volatile compounds removed by the distillation unit and processed and finally supplied as a pure drink water. And here is a collection of urine, and another waste is toilet is here. So life support system sometimes calculated by mass. If we use one-way system, initial weight is right, but as increasing mission time, the system mass is increased rapidly. But if we can recycle system, initial weight is heavy, but after long mission time, the increase of system mass is not so big. So after ISS, we are developing gateway, and JAXA contributes to the here. I have international habitation module, and inside of the international habitation module, blue part is JAXA will make. And especially here is a CDRS, carbon dioxide removal system. And here is the TCCS, trace contamination control system. So we are developing physical, chemical, environmental control and life support system equals home and space exploration. That's all. Thank you.
Sakurai Sensei. It's a very important to know for us, ECRUS, because the ECRUS is a fundamental, but not only for the life supporting the quality of life, it's based on his technology. Okay, so any question, any suggestion about this talk? I think some of you might be very, very important, but クロスさんとか大体いきなり振りましたけど。
Thank you, Mr. Sakura Sensei. So in addition to the scope of JAXA, who will take care of the other part of the ECRUS in the gateway system?
other part. This is a tank for gas or air.
Who are going to take care? So, yeah, you said that JAXA will take care of the red box only or total ecosystem?
Total, I have ESA designed, and JAXA supply this kind of machine or system.
Thank you very much.
You want to say something? Oh, yeah.
I'm sorry. So I'm just wondering, so the system is more closed on the gateway in terms of the chemical cycles and the material cycles, but how much waste is expected each year that is not recycled, material that is not recycled?
Actually, gateway is very small compared to ISS, 1/7 size. So actually, we cannot make a recycle system, one-way cycle. So, and 1 year, 12 months, manned mission is only 1 month. So we cannot prepare a recycling system. So waste is carbon dioxide 1 kilogram per person per day, and water is 2.5 kilogram per person per day.
So the reason I asked this question, so even with only 1 month of operation in a year, it's still a fairly large amount of material from a crew that is sitting near the moon. And I'm just thinking that material, there should be some kind of plan for how to take that material down to the moon rather than throwing it away or bringing it back to Earth, or because if you've transported it all the way to the gateway, and it's only another 2,000 meters per second to get it down to the lunar surface where it is gold. Maybe there should be some plan to take the carbon dioxide and the water waste and other waste down to the lunar surface and have it be available for lunar surface agriculture and activities. Anyway, I'm just thinking it's a shame to take it all the way to the moon, to the gateway, and then throw it away.
Yeah, thank you. Very interesting question. But unfortunately, I don't know. Maybe throw away on the moon is no, because planetary protection. So maybe in the space, but I have to check it.
Maybe it's a very valuable venture capital business.
Yes, interesting.
It's interesting. Thank you. I want to ask one question about the pressurized rover. How can you bring the ecosystem for the pressurized rover that Toyota is?
Yeah, pressurized rover. We are now thinking again. Actually, it's a very limited space and weight. So it is a very, very difficult to realistic vehicles. So it's on the way.
On the way. Okay. Thank you. So the future of the Toyota is defending his research. So it's a very important one. Thank you very much. Okay. So the next speaker is coming from deep sea. I think Mr. Fujinaga, please come in. Where is Fujinaga now? Oh, he was just coming back from the deep sea and to the surface of this. He's a professional diver. He is now a PADI professional instructor who has recently established official moon program in underwater. So any person who has a license in the undersea can apply his newly established course to certify walking in the moon under the sea. And this is very, very interesting combination. And he's also showing how difficult to have a blessing so he is now trying to simulate the difficult environment with limited amount of the oxygen and limited air, breathing air. So he is now offline with an ECRUS system. So it support his life. So he has only 10 minutes or 15 minutes for he can talk. So I don't know if I can listen his voice safely. Okay, please try. Thank you.
Okay. Can can you hear me? Okay.
We can hear you.
Okay, let me start.
Oh, you can respire.
Okay, let me start it.
Good respiration.
So, okay, good morning, ladies and gentlemen. This announcement, as Mr. Yamashiki announced it, I can't breathe any longer. So, well, let me do it. I'm so glad to be here to make a presentation at this special moment, Moon Village. But I have a small favor. Oh, I have a small favor to ask of you all that we're all here. I think we're all here to aim straight forward to the moon. And I think that I can see your eyes that we're looking forward to the moon. So I can see your eyes and even your heart looking up to the sky. But only at this few moments, I want you all to turn over your eyes from up to down to the deep ocean. So let's just see the simulated moon environment named space diving. And here's a story. When I go scuba diving, I several times hear these words from other divers that, oh yeah, diving is gonna be so fantastic that I always feel like zero gravity. True, maybe. Well, true that I agree that it really does feel like you are in space, but actually it's not it. An ocean in space, it can't be equal. You'll be caught from 1Z wherever you are. Then what lets you feel like you're floating is that when you got the best balance. The balance of the force of buoyancy and the force of the 1Z with your mass. And divers can control their buoyancy by supplying or exhausting the air from their BCD. The BCD is which I'm wearing like this. And interestingly, when you exhaust all the air from this BCD, you'll see some kind of like a 1/6 gravity situation. And here's a movie. Take a look at it. Kind of like a big jump. And another movie is like exploring the bottom of the water under the sea. So, space diving is, well, let all divers explore the simulated moon environment. And I divided this course into 3 levels. From bottom, space diving 1 and 2, 3. And the reason is clear that it is to guarantee its safety. Ocean is the extreme environment, which may amaze you with the fantastic physical experience, but don't forget that it's gonna be dangerous if you don't keep the standards or if you miss safety skills, you'll be easily dead. You'll be easily dead. So the top priority of this course is to stay alive, and no other thing could be more important than this. So therefore, I got an official approval from PUDI, which is the world's largest ocean exploration and diver organization. And according to this, each level is based on the certification levels. 1 from the bottom is for open water diver, and 2 is for advanced open water, and 3 is for rescue. And but here's a notice that this course is not only for PUDI divers. All divers who were certified by other diving organizations can apply, so don't worry. And during these courses, I've set several missions, samplings, navigation, and documentation, and rescue. And for this sampling, we're gonna pick up marine debris instead of coral reef or other marine resources. And after you collect debris, you can post a report on the international online platform organized by PUDI and marine biologists, so that your actions won't end up with just one action. It helps marine biologists research the amount of its degrees, and finally contributes to environmental preservation. And this space diving course is basically modeled after many things from NEMO mission report and human behavior performance competency model offered by NASA. And I've arranged it with precious knowledges and techniques what I've learned from technical diving. Are there someone else who knows technical diving? Except, yeah, you know. Well, technical diving is kind of different from general style. Most style will be done at open water. Nothing will be above your head, but at technical diving, we can explore at a closed overhead environment, like caves, wrecks, and ices, and even the extreme depth beyond 40 meters. These are an extreme environment that we have to be well prepared. We learn the mechanism of decompression and narcosis, oxygen toxicity, and above it, make their own gas plant. I have a short movie, what kind of technical diving we do. You see the double tank. That was a cool movie. And maybe I'm losing my air. I can't breathe so longer. So I should better end up earlier. But before ending my this moment, I'd like to let me tell you about my mind, even my heart to this course. The reasons I made this course to make our heart much closer to the moon, much more approachable to the moon, and let you all to remember that how oceans will be important. We humans, moon seems so far away, and even its distance makes us feel that it's somehow beyond our reach. Well, I think that's because we had no chance to experience how space or moon is going to be like. So we human recognize an event or a phenomena strongly from their own experience. So I came here to tell you, why don't we refocus on the ocean? So beautiful. I took this video at Seb Island. The place is mud water. You see the hammerhead shark. You love it.
Forehead.
Yes, this is the hammerhead. You see the diver is so close. And this was captured at Mikomoto. And this, remember, yes, the sperm whale. This year, this September, right? Yeah, we saw it. So what drives me is my own curiosity. Our ancients had pushed their boundaries with their curiosities. They walked through the desert, they climbed the mountains, passed through the forest, and crossed the sea. But remember that we're still in the past. We're now aiming to the moon. So I'm here to remind you that ocean will be the key. One of the answers will be in the ocean. And space diving, I believe, will let you know it. I'll be waiting for a challenge. Thank you for listening.
Thank you from the deep sea. Are you okay still? Do you have oxygen still? Or can you can answer
A
for
few seconds.
only once? Okay. So quick question, please. Thinking about his security. Any question you want to? Any person who is interested in space dive? Yeah. From myself. Are you really wanting to go to the moon, or you want to stay in the ocean?
I would like to go to the moon.
You want to
Yeah,
go
I'd
to
like
the
to.
moon, but how can you dive there?
How can I
you-
dive there? Gonna be a difficult question.
So he will dive in the space, or like by without water.
Well, yeah, it could be, but if I can go dive in the outer space, you have to make the marine ocean, the
Yeah.
space ocean.
Actually, there are many similarities between the space astronaut and diver, because they are restricted by the air, available air, atmosphere. So he has to bring his tank. Today, without tank, he is very, very difficult condition. But and then the decompression sickness is another important thing, because he has to think about decompression sickness when you up to the surface, because
Yes.
decreasing the pressure. It's the same things happens when the EVA or the astronauts happen. So there are many similarities. So why don't you try his newly established course and certified as a lunar walker? Okay. Thank you.
Thank you.
Thank you very much. So please come back safely without Please don't consume a lot of oxygen, right? Okay, thank you very much. Actually, the last speaker is today is also, he has problem. He's now flying from the different place to the, so he sent a video. So we have his presentation with the video. Let me introduce Ichimura-san, who is trying to survey about the circular material in the space, circular economy. Okay, please.
At the 7th Global MBA Workshop and Symposium. My name is Shuichi Chimura, and I would like to talk about the assessment of the current recycling system on the ISS and potential issue for the future human space exploration. And first, I would like to start with the background and issue. So this chart shows the launch mass of the resupply items to the International Space Station. Currently, the ISS relies on cargo delivery 10 times per year in average to supply water, food, air, and other science equipment. But as you can see here, in order to deliver just 30 tons of resupply items, 98.5 of the mass, most of it is the propellant, is discarded. And we can tell that it is very inefficient. Since ISS relies on this resupply system, it has a various negative effects in both physical and psychological, from supply to trash. Colors with light blue shows the life support system elements, and in case of a launch failure or launch delay, we can easily imagine that astronauts will face the shortage risk of air, water, and food. Colors with dark blue shows the quality of life elements. And for instance, we're not just talking about air, water, and food, but lack of clothing and also hygiene items such as towels, wipes, and lack of freshness of a variety of groceries, and wearing same kind of clothes. Those kind of items have a negative effect. And sometimes astronauts need to deal with the garbage smell and dead space due to the temporary storage of garbage. And in the past, there are many studies trying to discussing about how to improve the life support system, like improving the recycling rates. But in order to achieve the sustainable human space exploration, here we would like to focus on the quality of life elements as well. And when we talk about QOL, we're talking about clothing in order to live in a society, hygiene items to keep us clean, and healthcare items to stay healthy. And since we are here to discuss about the moon village or the moon exploration, we also need to consider the cost and delivery time to the moon. It is said that it will require more than 10 times of cost and much longer delivery will be required to deliver items from Earth to the moon. So from that perspective, it is obvious that we need to develop a circular economy or circular system in order to maintain a sustainable lunar activity. So what is the current recycling status on the ISS? This chart shows the current recycling ratio of each element on the ISS. We can see that the life support systems elements such as air and water, the technology has been improving, and it is reaching a very high level of a recycling ratio. And just to point out, the air, 91.6% is we're talking about, this is due to the air leakage out of the ISS. And if we talk specifically about the oxygen recycle rate, it's nearly like 51%. But on the other hand, like food, clothes, and other quality of life elements, there are no systems on board existing at this time. and we need to keep resupplying those items from Earth. So we can easily imagine that we need to keep resupplying these items in order to maintain the life and also the quality of life. But the question here is, are there any other items that need in order to maintain this recycling system, or in order to maintain the quality of life elements, other than like air tank or water bags? So what we did was gather the historical data of the ISS, and also from the duration of October 2017 to 2020. And in average, there were like 5.7 crew members on board, 66,000 kilograms of mass were launched, and there were 31 missions during this duration. And we sorted out all of the items to whether it's going to be like a life support system elements or the quality of life elements. This chart shows the result of the analysis, and this pie chart shows the ratio of the air supply, water resupplies, and the food resupplies. And the gray portion shows the resupply items, I mean the reserved items, such as if we focus on the air resupplies, this gray portion, which counts for 22%, it includes the gas tanks of nitrogen and also oxygens. So we can easily imagine that these gas tanks are kept shipped to the ISS. But as you can see in this blue portion, in order to maintain this air recycling system, we need to keep delivering these filters, air filters, and also maintenance kits, and also other monitoring control spare items in order to maintain this air recycling system. For water resupplies, 76% is the water tank, which we can easily imagine, but the other 24% is the toilet hardware and also the waste containment, which is consumables and spare items. And for food, currently we don't have a recycling system, but the food, 81% of the food items that has been delivered will be consumed by the astronauts. But the other 19% will be discarded because it's the packaging and also food that has adhered to the packaging itself. So here we can tell that from 19% to 78% of the supply items are consumables and spare parts. And we also, when we talk about the quality of life elements, here is the items that shows the clothing. And on the left-hand side, theoretically, it requires 0.21 to 1.69 kilograms for each crew and per day. But the fact is that only 0.396 kilograms per crew and day has been delivered. So, and as a fact, from the interview from the JAXA astronaut, which is mentioned in the JAXA Space Life Storybook, we can tell that astronauts have to wear same clothes, and that includes the underwears for days and sometimes for a week, depending on the type. And it, like the smell of the underwear becomes bothersome for after 3 days, and the sense of the cleanness and freshness has gone away. So we can easily imagine that that this delivery system leads to a very low quality of life. And talking about hygiene elements and healthcare elements, 60% of the hygiene elements are towels and wipes. And this is the one-time use. And nearly 50% of the fitness items is the equipments of the exercise, and those are spare parts. So we need to keep shipping these items as well. As a conclusion, we figured out that the recycling life support system is not just launching about the water tanks or the gas tanks, but there's a significant amount of spare items and consumables required to maintain those recycling system. So we need to design to minimize those spare parts and consumables, or to develop 3D printing technology in order to develop those spare items on board the ISS. It is obvious that we need to develop a food production system, and probably that requires minimum amount of water. And the third finding is that the QOL elements, such as clothing, towels, and wipes, are not recycled. So probably laundry or recycling those clothing and towels could maybe contribute to the better quality of life. And that is end of the presentation. Thank you very much.
Thank you. This is, I think it's one of the interesting talk about discussing about the supply chain for the ISS and how to improve the efficiency, because most of the clothes are just junk, and it will cost a lot of money. And to maintain the QOL is very important, but it's difficult, that current status, spending a lot of things just for sending there. But unfortunately, he is not here, so we cannot have a deep discussion, but I think the discussion should be in the future. Now, we would like to ask John to introduce the MVA Moon Village Association video, because he's a
Welcome to the third Prima Moon Initiative for Moon Village Generation in honor of Dr. Alexander Degtyaryov.
So one of the projects of the Village Association is a project to mentor new players who are interested in new concepts for the lunar activities. And this has been organized under the name Promo Moon by the team led by Oleg Vintovsky, who is on the MVA board of directors, and it's from Yuzhnoye in the Ukraine. And so we provide strong support to this activity. And they made a short video. It's in honor of, you'll see, recently passed senior leader from the founding of Yuzhnoye. And so if you would please give your kind attention, this will tell you about this program. Thank you so much.
Welcome to the third Prima Moon Initiative for Moon Village Generation in honor of Dr. Alexander Degtyaryov. At the end of 2021, the Moon Village Association, in cooperation with the leading Ukrainian space engineering company, Yuzhnoye State Design Office, organized the first Prima Moon Initiative. This competition is a special form of recognition of Alexander Viktorovich Degtyaryov, General Designer, General Director of Yuzhnoye State Design Office from 2010-2020, an expert in aerospace technology with a global vision, a talented leader, and a supporter of ambitious endeavors to conquer the cosmos. Interplanetary missions and the creation of human settlements on the Moon and Mars became not only his cherished dreams, but also defined the direction of technology development for the company, which he successfully headed for a decade. The main objectives of the initiative are to build up the potential of new players in the space market, improve and increase the availability of innovative lunar technologies, and provide the support in the concept demonstration to initiative groups, enthusiasts, and startups from all over the world. The competition is held annually. Its main focus on technical concepts and new solutions related to lunar technologies. As part of the competition, a group of experts will select the best technical solutions from among all the participants to provide voluntary and free experts assessment of the concept during personal mentoring sessions. The competition will be a very interesting and rewarding experience for everyone who dreams of contributing to the exploration and colonization of the Moon. The competition has already been held twice, with 24 participating teams from 12 countries. The winners of previous initiatives. The first Prima Moon initiative, Frank Koch orbit recycling startup, with the project Lunar Building Materials produced based on recycled space debris, Germany. Kunal Kulkarni, VEPS student team, with the project Volatile Extraction Technology on Planetary Surfaces, Germany. Elliot Roth, Spira Incorporated startup, with the project Technology to Efficiently Generate Food and O2 and Remove CO2 During Space Missions, United States. The second Prima Moon initiative, Samer El Sayari with the OSIS and IRIS project, Egypt. Colin Lennox, Eco Islands LLC SME, with the project Resource Extraction from Solution using Self-Organizing Wetland Bioreactors, SOWBS, United States. Haralampos Cosmos, Lunar Cargo PC startup with the Lunar Cargo Project, Greece. The Prima Moon Initiative's award and closing ceremony was broadcast live on the MVA's YouTube channel and featured members of the Moon Village Association's Board of Directors, representatives from Yuzhnoye SDO, and the winning teams themselves.
Thanks to the extremely constructive feedback from the initiative, especially from the experts from the Ukraine Yuzhnoye State Design Office, we developed further our concept.
First of all, let me take a moment to express my gratitude to Prima Moon Initiative for the motivation, inspiration, and mentorship that helped me to dream, innovate.
This year, the submission of applications for participation in the initiative began on October 31, the birthday of Alexander Dekturov, and will last until December 24. The finalists of the competition will be announced on April 10, 2024, the 70th anniversary of Yuzhnoye SDO's foundation. 3 winners will be selected on June 20 to receive free of charge B2B mentorship on their projects during mentoring sessions to be held between June 26 and July 16. The award and closing ceremony for the winners of the competition will be held on July 18 as part of International Moon Day. Yuzhnoye SDO and the Moon Village Association invite everyone, from enthusiasts to professionals, to take part in the 3rd International Prima Moon Initiative for Moon Village Generation in honor of Alexander Dekturov. Follow the Prima Moon Initiative news on the website and other MVA Internet resources using the hashtag PrimaMoon2024. We wish everyone the best of luck in winning the competition.
International competition, and it's open now, and it will stay open for another 2 weeks. It's intended for entrepreneurs or innovators who would like to propose some new concept for lunar exploration or development or resource utilization. And there's a team of experts who will evaluate all the submitted proposals. And the prize, there's no money or anything, but the prize is then your concept, if it is selected as one of the 3 winners, you will get private consulting and evaluation and commentary on your idea to give you the benefit of feedback from space professionals on the merits of your idea, how it could be improved, and so on. So that's the Prima Moon Initiative, and you have 2 weeks left before the deadline for submission for this year. So please consider participating. Thank you.
Thank you. So how about space diving course? Who is here? Yeah, he can propose, right? So something. Okay, thank you. Now we have a time for the announcement from the organizers. So can you?
Hello everyone, I am Aki Yumi from Amulapo Company. and I will explain you about after this symposium end. And let me briefly explain the flow of the schedule. So most of you guys are mostly Japanese will be this left schedule, and foreigners will be the right schedule. And this right schedule will be leaded by the Miura sensei. So please follow him. And then let's explain the symposium and 2:50. And then we have the bus to the sand dune in 10 minutes. So do not miss the bus at the 22:50. And then from sand dune, we will briefly look at the sand dune, and then again, the bus will lead you to the Sand Museum. And after looking around the Sand Museum, you will go to the outreach venue, which is very close to the Sand Museum. And then farewell cocktail in the same place. Then after this, we have the simulated astronaut activity using an air glass, which is occurred in the sand dune again. So here is the bus again. And if you have to go back to home in between or somewhere else, please tell me about when you have to go back to Tottori. For example, we have the bus from Sand Dune to the Tottori station. And also after the farewell cocktail, we have the bus to the Tottori station too. Okay, so could you raise your hand that if you want to go back just after symposium end? Okay, 3. Okay, how many of you will have to go back after, like, before the outreach? Before the outreach, okay, several. So, okay, all right. So let me express that in detail. So, okay. Just after the symposium, we have the bus 2:50 to Tottori Sand Dune. And then if you want to go to Tottori station, do not get off the bus. And then the bus will lead to the Tottori station after the Sand Dune. Then this is the bus 1. And please ride the bus 1. And bus 1. So she is will ride with you on the bus 1. Shimizu-san. And after the Sand Dune, we have Sand Dune, 3:20, we will move to the Sand Museum. And then if you skip this Sand Museum, you can go to the Tottori station. Okay. And after the outreach, if you skip the simulated astronaut activity, there's also the bus at the 7 to the Tottori station. This is bus 2. And this is very confusing. And if you want to ask us, please ask me or Shimizu-san or any of staffers here, and we will let you know. Okay, so this is a general schedule. Do you have any questions? Okay. Yes, farewell cocktail is. Yes, that's yes, we have it. Yes. 7. Start bus. Yeah, this is after the farewell cocktail. Yes, outreach venue. Yes, that's right. Same. That's right. So this is, hi. Okay. Right. Okay. And then now it's lunchtime. Then we have the lunchtime outside, besides the lunar terrace. Then the support staff, they will lead you to the places. Okay.
Thank you, Okabe-san. Thank you for wrapping up today's morning session. And we have an afternoon session just after the lunar test. So enjoy lunch. See you again. Thank you.
Hi, it's time to start the academic session now. So how was the lunch? Okay. And how was the weather? Yeah, this is abnormal. Yeah, usually we have snow in this season. Yeah. Yeah. Yes. Yeah, but I haven't experienced this kind of weather in December. Yes, but it was very fortunate for us. Okay. So in this session, we have 4 presentations. And I forgot to introduce my academic background when in a opening ceremony because I became a bit nervous. So, and I am an agronomist. I'm working on I am trying to make a wheat variety that can adapt to the very dry area. Yeah, so I think in moon, we have to produce food. Yes, but production of the food is not so easy. Yes, and today the first talk is about the this kind of title, and you see, I am agronomist, so I am usually watching the plant over the ground. But it's still unknown about what is happening underground. Yes, so the first presenter is by Dr. Teramoto, and his title is a carbon cycle in terrestrial ecosystems. Okay, so please.
Thank you very much, Professor Tsujimoto. My name is Munemasa Teramoto, and nice to meet you today. And I'm going to talk about carbon cycle in terrestrial ecosystems today. And my research background is I focus on the terrestrial carbon cycle, and my research area is ecosystem ecology. And mainly focus on the research for the greenhouse gas emission and absorption in terrestrial ecosystems, mainly focusing on the soil. And previously, I focused on the forest ecosystems. This picture is a survey in Malaysia. But after I came to the arid land research center in Tottori University, I focus on the arid land ecosystems and also coastal dunes. And my keyword is carbon cycle and global warming and greenhouse gases, soil respiration, and arid ecosystems, forest soil carbon dynamics. First we talk about the global carbon cycle. Globally, carbon cycles in the marine and the atmosphere and the terrestrial ecosystems have several various forms. And main types of carbon in the atmosphere, carbon dioxide and methane. This carbon cycle is also calls for a very remarkably concern with undergoing global climate change and global warming. At the same time, today I myself do not focus on the space, but this global carbon cycle may be beneficial for the future because understanding the detailed mechanism of the carbon cycle, especially in ecosystems in marginal land, might be beneficial not only from the viewpoint of mitigation and adaptation for ongoing climate change, but also for building an ecosystem outside the Earth. So I'm not related with the space research, but please listen my presentation. And in the terrestrial ecosystem, there are several types of carbon emission and absorption. For example, trees and vegetation absorbs heavy amount of carbon dioxide from the atmosphere as photosynthesis. On the other hand, the plant above ground part also and the root have a emission, CO2 emission as plant respiration and the root respiration. At the same time, microbiota in soil also decompose the soil organic carbon in soil, and the heterotrophic respiration, we call it. And this microbial decomposition, that means heterotrophic respiration, and root respiration, the sum is called soil respiration. Of course, we have a heavy amount of anthropogenic emission as a fossil fuel emission and land use change. However, if we compare the magnitude of the emission, global soil respiration is more than the anthropogenic annual emission. So, and this global climate change and artificial disturbance also influence on this kind of terrestrial carbon fluxes and carbon cycle. So I firstly introduce how much carbon is released to the atmosphere every year by human activities. This is the value written in the IPCC 6 report that is recently published in 2021. According to the report, the average emission from fossil fuel is 94 gigaton carbon per year. This is the average from 2010 to 2019. On the other hand, and there is also land use change calls for a 1.6 gigaton carbon per year. So the sum of anthropogenic emission is 10 gigaton carbon, more than the 10 gigaton carbon per year. So on the other hand, global soil respiration, I talk about the global soil respiration. In the natural ecosystem, soil respiration is the second largest carbon flux. That means the carbon emission in the terrestrial ecosystem. The first biggest flux is the photosynthesis, that is absorption of the vegetation. But the soil respiration is the second. And a recent publication, until now, there are several types of global estimation for soil respiration, but Jian et al. Recently synthesized those publication value that is roughly from 70 and 100 gigaton carbon per year. Even though there is a very large uncertainty for the global estimation for the soil respiration, but the magnitude and the flux value itself is larger than the anthropogenic annual emission. So this is a very large carbon emission from the soil. According to the very famous paper published in 2010 in Nature, this paper suggested a gradual increase of global soil respiration from the 1990, the past 2 decades. This is the cited so many times. As like this, there is a large uncertainty of the ecosystem feedback to climate change and artificial disturbance. When we think about the global climate change and a precise estimation for the future environment, it is also important to understand the magnitude and the feedback. Especially, soil contains so much amount of organic carbon, and soil organic carbon dynamic is a key for the future climate change. So this is the map for the worldwide observation for the soil respiration until now. This is the, I cited the map of the database, version 5, the very famous database is published from here. And you can notice the bias, the regional bias of the observation data all over the world. Yes, the flux research area, there is so much observation data in North America and Europe, and also recently in China and Japan, but not so much data around Central Asia and other regions than Africa. So this regional bias also caused the large uncertainty. So I myself personally interested in the soil respiration and carbon flux in arid ecosystems because this region is usually the data is limited. So I myself concerns the Mongolia country, and from the recent 2 previous years, I focused on the 2 main projects. The one is the seasonal warming experiment in one study site in Mongolia, using this kind of the open top chamber. This open top chamber can cause for the artificial warming of the grassland ecosystem. And I measured the carbon emission and absorption and examined the influence of seasonal warming on the productivity of this kind of ecosystem, grassland ecosystem. And another project is examining the grazing effect on soil respiration in 3 grasslands in Mongolia. The purpose is to examine the influence of grazing on soil respiration in Mongolia from 2022 to 2023. Today, I briefly show you the simple result of those surveys. So grazing is very important agricultural form in Mongolia. And according to the one report in Mongolia, more than 50% of land is already degraded somehow, partly because of the overgrazing. So the purpose of this study is to analyzing the influence of grazing on soil respiration. I call it RS, the soil respiration is RS. Examine which factor, the biomass, temperature, and precipitation are important for the magnitude of grazing effect on soil respiration. These study sites, the 3 grassland sites in Mongolia, I made a survey with collaborator. This is the Fustai grassland in 2022 August. In Fustai, we just made a survey only in 2022. And this is Mandargobi grassland. We conducted 2 times in 2022 August and 2023 August in Mandargobi and in the central Mongolia. This is the southern part of Mongolia and near to the Gobi Desert. And also made a 2 times survey in 2022 and 2023. This is the simple diagram for the plot design. Firstly, we watch the vegetation because the collaborator is the plant researcher. So by watching the vegetation, we separated the degraded site and control site with little influence of grazing. And we set the quadrat, 5 meter quadrat, 3 replication in each site. And we measured the soil respiration 3 times in 1 quadrat. And we also took the biomass sampling above ground and we measured the dry weight of the vegetation, above ground vegetation part. And we also took the root biomass until the depth of 20 centimeter in 1 point in 1 quadrat. And just we compare the soil respiration value between the degraded site and the control site. At the same time, with the soil respiration measurement, we also measure the soil temperature and volumetric soil moisture at the same time. We just use these kind of portable devices to measure the soil respiration. This is the soil respiration measurement system, and volumetric soil moisture and the soil temperature. The principle for measured soil respiration is very simple. And we just put the container on the surface of soil and keep it for several minutes. During the several minutes, in my research, only 2 minutes. During the 2 minutes, x-axis is the time and y-axis is the CO2 concentration inside the chamber. We can observe the linear increase of CO2 concentration inside the chamber sampling air. Just calculating the slope of this increase, linear slope, we calculate the speed of soil respiration. This is called chamber method, and this container is called chamber. And I show you the picture in control sites in Fustai and Mandargobi and Burugan, and the degraded site. The bottom picture is a degraded site in Fustai and Mandargobi and Burugan. Especially in Fustai and Mandargobi, we show some perennial species, the steeper Krilobi, mainly appear in the control site in Fustai and Mandargobi. This kind of the perennial herbs is only appeared in the control site. And this is the result and root biomass data in each site in August 22nd. Root biomass was significantly larger in control site, that means the green bar, compared with degraded sites in Fustai and Mandargobi, but there was no significant difference in Mandargobi because the deviation was so large in this site. And this is the soil respiration data in each site in August 22nd. Y-axis is soil respiration. And soil respiration was significantly larger in control sites compared with degraded site in Fustai and Mandargobi, but there was no significant difference in Burugan. So the tendency in the 2023 is also same. We just made a survey in Mandargobi and Burugan only. This is the root biomass in Mandargobi and Burugan in 2003. Also, the same as the root biomass was significantly larger in control site compared with the degraded site in Mandargobi. And the result for soil respiration is the same as 2022. Soil respiration was significantly larger in control site compared with degraded site in Mandargobi, but there was no significant difference in Burugan. So, as a summary, degradation of grassland ecosystems due to grazing decreased soil respiration partly because of the decrease of root biomass in Fustai and Mandargobi. But there was no significant difference in Burugan. So now we need further analysis for the reason why soil respiration didn't change among the control site and degraded site in Burugan. This is I show you only the simple part of our result. Thank you very much for listening.
Thank you, Dr. Teramoto. Question?
Sorry, I missed a little bit about the initial part. My question is about the definition of the soil, respiration of the soil, right? So if you have like anaerobic digestion under the ground, and then will it be a kind of it's a soil respiration? It's not soil respiration, or is it for the digestion of the carbons? Production of carbon, are you determining about the carbon dioxide emission will be the soil respiration? Or if you have some kind of if you put the air or if you put the oxygen inside of the ground or not, will it be affected? Because if there is no oxygen, there are hydrogen sulfide might be the different components coming from the soil. So those conditions, so you have to, in order to produce carbon dioxide, you have to put the oxygen inside, or if you just don't do that, will it be only hydrogen sulfur is coming, or still there are carbon dioxide is coming from the soil?
Thank you very much for the question. First of all, the definition of soil respiration is the carbon dioxide emission from the soil surface. And we cannot include the carbon dioxide concentration inside the soil. So the definition is just as a result of several reasons, microbial decomposition and root respiration. But we just measure the emission from the soil surface is the soil respiration. And as Professor Yamashiki said, if we put the oxygen inside the soil, it will be just my imagination, but it will be increase the soil respiration because the oxygen is limited in the soil. But I myself is the ecosystem researcher, and we avoid the disturbance as possible as we can to understand the natural state. Yeah, so we just put the rings and put the chamber and just measure the soil respiration usually. Yeah.
Thank you, Dr. Teramoto. Okay, so we move to the next presentation. Thank you very much. The next presenter is Professor Kuroda, who is working in a faculty of engineering in Tottori University. Okay. Okay, please.
Thank you very much, Professor Tsujimoto. I'm Tamotsu Kuroda. My major is concrete engineering. Today, I would like to talk about an example of a study on durability of reinforced concrete structures. Please forgive me if the content is not space-related. Reinforced concrete structures are durable structures. However, concrete structures may deteriorate prematurely due to the causes shown here. These are deterioration mechanisms of reinforced concrete structures. First, let me explain about carbonation. Carbonation is deterioration phenomenon that occurs when atmospheric carbon dioxide penetrates into concrete, causing the calcium hydroxide in the concrete to change to calcium carbonate. Concrete has a pH of about 13.5 and is strongly alkaline. Reinforced concrete structures are reinforced by placing rebar in the concrete. Rebar in concrete is restaurant to last because of the strong alkalinity of concrete. However, carbonation can lead to corrosion of the rebar. Rebar corrosion occurs when the pH of the concrete falls below 11. When rebar corrodes, its volume increases approximately 2.5 times. This volumetric expansion of the rebar causes cracking and spalling of the concrete. Next, I will explain salt attack. when chloride ions above a certain concentration are present around the river in concrete, the river will corrode. As explained earlier, when the river corrodes, its extreme pressure causes cracking and spalling of the concrete. One of the causes of chloride ion supply in concrete comes from the materials used in the concrete. In addition, in environments where seawater and anti-freezing agents come in contact with the concrete surface, they penetrate into the concrete and increase the chloride ion concentration. Next is frost damage. Concrete deteriorates as water in the concrete permeability, repeatedly freezing and thawing. The expansion pressure as water freezes damages concrete. This deterioration is called frost damage. Frost damage is a deterioration that occurs in cold climate. When frost damage occurs, cracks appear on the concrete surface as spalling occurs, which is a gradual removal of the concrete surface. In addition, small holes may form on the concrete surface. These holes occur because water in the aggregate near the surface of the concrete freezes and causes aggregate to expand. This phenomenon is called pop-out. Next is chemical attack. Chemicals penetrate the concrete, alter the hydration product, and the cement hardened body loses its bonding strength. As a result, concrete is gradually chipped away from the surface. This deterioration phenomenon is called chemical attack. The main chemicals that cause chemical attack on concrete are strong acid and sulfate. Next is alkali silica reaction. Alkali silica reaction is called ASR for short. Alkali silica gel is formed by the reaction of certain silica minerals in the aggregates used in concrete with alkali hydroxide is the concrete. These are alkali silica gels. These are alkali silica gels. These alkali silica gel absorbed liquids in the concrete and expand. This expansion pressure causes a crack in the concrete. This is called alkali silica reaction. Not all aggregates will cause an alkali silica reaction. When an alkali silica reaction occurs, cracks of large width and steps in the cracks may occur, as shown here. These are the deterioration mechanisms of reinforced concrete structures. The following are some examples of studies related to these deteriorations. Next, I would like to talk about the application of the cathodic protection to reinforce concrete that may suffer from combined deterioration due to salt attack and alkali silica reaction. Regarding the salt attack, explained earlier, cathodic protection is the most effective repair method to stop the corrosion of rivers. In the cathodic protection, a direct current is applied between an anode attached to the concrete surface and the rebar. The corrosion reaction of the rebar can be stopped by lowering the rebar's potential by making it cathode. However, if aggregates that cause alkali-silica reaction are present in the concrete, the cathodic protection may accelerate deterioration due to alkali-silica reactions. As shown in this figure, sodium and potassium ions in the concrete are attracted to the area around the rebar by using the rebar as a cathode. This is because sodium and potassium ions are cations. On the other hand, hydroxide ions are generated in the vicinity of the rebar due to electric current. As a result, the alkali-silica reaction is accelerated due to the increased concentration of sodium hydroxide and potassium hydroxide around the rebar. This figure illustrated the phenomenon. After the reinforced concrete is energized, the section here is cut and divided into 16 specimens. The alkali concentration of these samples in the analyzed. These figures show the result. In the sample before energization, the alkali concentration distribution is a cross-section is uniform. In the sample before energization, the alkali concentration distribution is a cross-section uniform. On the other hand, alkali concentration increases around the rebar after energization. Thus, alkali in the concrete moves in the direction of the rebar when energized. As shown in this figure, the larger the current density, the more alkali is transferred during the same energization period. The figure shows the relationship between expansion due to the alkali-silica reaction and current density. Thus, the expansion increases with increasing current density. However, above a certain value of current density, the expansion decreases with increasing current density. The properties of alkali-silica gel vary depending on the ratio of its chemical components. It is believed that the ratio of silica to sodium in alkali-silica gel, the more fluid the alkali-silica gel becomes, and the smaller the expansion pressure. As the current density increases, excess alkali accumulates around the rebar at an early stage, and its concentration increases there. The amount of alkali in the alkali-silica gel becomes excessively high, and the alkali-silica gel becomes fluidized. As a result, the expansion was smaller when the current density was excessively large. Considering this phenomenon, we saw that supplying a large current density before applying cathodic protection to suppress the expansion caused by the alkali silicon reaction. As shown in this figure, cathodic protection was applied after supplying a large current density. The current density applied in cathodic protection is 30 milliampere per square meter. Before applying the cathodic protection, the specimens were energized at 1 ampere per square meter for 8 weeks, at 2 ampere per square meter for 4 weeks, and at 2 ampere per square meter for 8 weeks. As shown in this figure, the specimens that were supplied with a large current density before cathodic protection showed it a greater suppression of expansion than the specimens that were not supplied with a large current density. This is a specimen that did not supply a large current density. These are the specimens supplied with large current densities. This figure shows the rate of suppression of expansion by supplying a large current density. A larger suppression ratio indicates a higher suppression of expansion. When suppression ratio is 50%, the expansion is shown to be halved by supplying a large current density. This figure shows that the large current density supplied to and the longer the energization period, the more effective the suppression of expansion is. Supplying a current density of 2 ampere per square meter for 8 weeks before applying cathodic protection has resulted in 80% suppression of expansion. We believe that this method of energization may effectively apply cathodic protection to reinforce concrete structures that are susceptible to alkali-silic reaction. As mentioned above, we are engaged in research to improve the durability of concrete structures. That concluded my presentation. Thank you for kind attention.
Well, thank you very much, Dr. Kuroda. Any question?
Thank you very much for the interesting presentation. My question is that if we use the concrete in somehow the space or moon, what kind of the problem can occur, mainly expected for the use of concrete in the outside of Earth? If you have any information, please teach me.
Thank you for our question. I think application of concrete on moon, there are some problems. One problem is moon surface temperature of moon. Surface temperature of moon differ approximately 300 degrees between day and night. concrete occurs crack with surface temperature, large surface temperature difference. This is an important problem. More problem is Moon's gravity is 1/6 that of Earth. Concrete is concrete can not mix. This is a problem. Thank you very much for.
I'm Takeshi Taniguchi from Aridland Research Center, and my major is microbiology and ecology in dryland. So yeah, today I'd like to start from the explanation of dryland. Dryland is a dry region, as you know, and defined by aridity index calculated by potential evapotranspiration and precipitation. And in Japan, Japan is a humid region because of the huge rain, but in the world, more than 40% of global land area is dryland. And more than 30% of world population is living in the dryland. And also in the aspect of food production, dryland is very important region. But dryland is frequently, dryland is degraded by the fragile ecosystem. And a part of dryland with poor vegetation is called desert. This is a distribution of a very famous desert in the world. And the definition of desert is not clear, but in the broad sense, desert is the arid and semi-arid zones defined by aridity. And in the narrow sense, true desert is hyper-arid region. And so in total, arid, hyper-arid, arid, and semi-arid regions make up 33% of total land area. And the desert is a very extreme environment, as you know, and this is because high solar radiation and temperature fluctuation is very variable, and water availability is low because of low precipitation and high water evaporation. And also by the low water availability, plant growth is, plant production is limited, so soil nutrition is also very poor. And also by the high water evaporation, salt such as sodium accumulate on soil surface and pH is increased. So the dry desert is a very harsh environment. But even in such environment, microorganism is living. In the when the aridity is very high, autotrophic microorganisms such as cyanobacteria can live, can survive. And in milder condition, this kind of biological soil crust formed by cyanobacteria, lichen, and moss are observed on the surface soil and fix carbon and nitrogen and create some soil. And in more milder condition, a plant can survive, and plant-associated microbes become dominant. And in this kind of ecosystem with a little bit more resource like carbon, nitrogen, and water, in such environment, heterotrophic microbes become dominant. And for me, I focus on this kind of ecosystem. And In the plant ecosystem, a plant photosynthesizes carbohydrate and provides a carbon as litters and root exudate with microbes. And decomposing microbes use litters, and rhizosome microbes use this kind of root exudate, and the amount is root exudate is calculated as 10 to 30% of the carbon fixed by a plant. So the amount is a little bit huge. And some of the nutrients become inorganic nutrient and used by the other organisms, including plants. And some of the nutrient is fixed by living and dead microbes. And we call this as microbial immobilization. And from this process, some of nutrients become inorganic nutrient again, or fixed in soil as long-term soil stock. This is a process. And in this process, I mainly focus on the rhizosome microbes and these endophytic microbes. And so now I would like to talk about the rhizosphere and endophytic microorganisms. And actually, when we take plant from root, soil attached to root. The soil attached to root is called rhizosphere soil. And microbes live in the soil is called rhizosphere microbes. And microbes live in the root is called endophytic microbes. These are pictures of the microbes. And these microbes have interaction with plants, neutral or positive or negative. And as positive effect of effective for plants, plant growth, nutrient uptake, stress tolerance, and disease resistance are enhanced by this kind of microbes. And for soil, by the interaction between the plant and microbes and soil mineral, soil aggregation, carbon accumulation, nutrient accumulation, and water holding capacity is increased. So the plant rhizosphere and endophytic microbes have a high potential to engineer plant and soil. And this is one of the interesting research about the interaction between the plant and plant microbes. And they also examine the relative humidity and temperature of this plant in Namib Desert. And this is a relative humidity of rhizosphere soil and non-vegetated soil, of surface soil and subsurface soil. Relative humidity is higher in rhizosphere soil compared to non-vegetated soil. This is the temperature. Temperature is lower in rhizosphere soil compared to non-vegetated soil. So it means that in this kind of desert, rhizosphere environmental condition is mild, and a plant may provide this kind of good condition for microbes. And the author also examined the functional features microbes living in rhizosphere soil by shotgun metagenome analysis of the soil, non-vegetation soil and rhizosphere soil. And as a result, they evaluated the genes, biofertilization-related genes, biopromotion genes, bioprotection-related genes, and biotic competition genes of microbes. And this is a non-vegetated soil, and this is a rhizosphere soil, and genes related to biofertilization, biopromotion, bioprotection, and biocompetition is increased in rhizosphere soil. It means that microbes with plant growth promotion traits are concentrated around roots. And also, as I talked, rhizosphere is a good environment for microbes. So microbes should have competitiveness to establish around roots. This is a feature of the functional feature of rhizosphere microbes. And next is about the functional feature of endophytic microbes. For this, actually, endophytic microbes is the subset of rhizosphere microbes. From the rhizosphere microbes, some microbes can enter roots. For the research, we examined the endophytic microbial features in coral desert. And as a result, in winter, gram-negative bacteria and nitrogen-fixing bacteria are dominant. In summer, gram-positive bacteria and avascular mycorrhizal fungi are dominant. Actually, nitrogen-fixing bacteria, most of the nitrogen-fixing bacteria is the gram-negative bacteria and have good adaptation to wet conditions. On the other hand, avascular mycorrhizal fungi is strong for drought and have tolerant to drought conditions. So plants seem to differentially use the beneficial microbes that have adaptation to the environment. And also, we analyze this kind of network analysis and find module hub microbes. That was streptomyces. This microbes is known as the plant growth promoting and have high drought tolerance. So now we conclude that plant root endophytic microbes responded to environment, but microbes with effective function for plant was selected. So that is a thing we are considering. And from the result, there may be the positive relationship between the microbes and plants. To confirm that, we collect soil from the desert and dilute soil by sterilized soil and check the plant growth. And low dilution soil have the much active microbes. In the condition, plant growth was good. It means that the plant and microbial relationship is positive in the natural desert. So in the natural desert, this kind of good relationship is maintained. And so from these relationships, I think that knowledge and microbes from healthy desert ecosystem will be effective to enhance microbe effect on plant for ecosystem restoration and sustainable agriculture. So this is like good reference to use. And from now, I talked about the good desert, but some ecosystem is degraded. And in such condition, microbes and plant relationship is degraded. Desertification is land degradation in dry land, and defined as desertification is land degradation in arid, semi-arid, and dry subhumid areas, resulting from various factors, including climatic variations and human activity. And during the desertification process, by the water erosion, wind erosion, and salinization, surface soil is lost. But the surface soil include plant seeds and soil nutrient and microbes. So when the surface soil is lost, it leads to the reduction of soil function. Then degraded land do not recover by itself because of the poor nutrient and water availability. So in such environment, we have to assist. And use of microbes is one of the options to enhance the activity. And this is an example of the restoration with microbes in Kubuki Desert in China. In this case, we used Pinus tabulae as vegetation tree. And actually, in the Kubuchi Desert, there was very little fungi in soil. But so we focus on the plantation site of the Pinus tabulae near to the desert, and then check the microbes, and it contains many fungal species, including effective ectomycorrhizal fungi. So we inoculate this soil to the Kubuchi Desert. And for the experiment, we set three treatment: no soil addition and fungicide treated plantation soil addition. It's in the treatment, we killed fungi. And non-treated plantation soil addition, it includes active fungi. And after 1 year, in the non-treated plantation soil addition treatment, the plant dry weight was very good. And also the effective mycorrhizal colonization was also very high. And we can get good correlation between the mycorrhizal colonization and total dry weight. So plantation soil inoculation with good mycorrhizal fungi promoted mycorrhization and plant growth. So yeah, it already suggested by another researcher, but microbial inoculation is effective for restoration in degraded land, including desert. So, but a problem is that still we don't know how to find good microbes. That is, still problem. And actually, most of researchers use single microbial species for restoration. But such one use of one species is unstable in the natural conditions. So ideally, it's better to use the combination of microbes. But it is very difficult to find what kind of combination is good for restoration. So to solve it, I did this kind of preliminary research to predict effective endophyte. In the research, we did research in, we examined sorghum in Sudan and get the and measure the shoot height like that as plant growth parameters, and also collect root and analyze the endophytic fungi and bacteria by next generation sequencing. And then try to predict by this kind of correlation, a plant growth parameter and number of sequence read of each species. And also we try to make this kind of micro occurrence network and try to detect hub microbes. By this kind of analysis, we try to predict effective microbes. But this is just prediction. So to check that, we also isolated fungi from sorghum roots and inoculate the microbes to sorghum. These are the microbes used for sorghum. 10 fungal species, bacterial species, and B2, B14, B22, and B23 is the plant growth associated by this prediction. And B14 and B22 was hub microbes. And this is the result. B14 and B22 and B23 enhance the plant growth compared to control. So this kind of prediction by plant growth effect and network hub may be effective. This kind of So now, as a next step, we are doing additional research and confirming this prediction, and also try to predict a microbial consortium also. This is like a summary of this presentation. In our research, we can find positive relationship between the microbes and plant in natural desert. So by examining the field and field research and experiment and check the relation between the microbes and the plant. We may be able to predict the adaptability and tolerance of microbes to environment, and also can predict, may be able to predict functional trait of each microorganism and functional consortium microbes. To check that, we need to isolate and inoculate single and multiple microbial inoculation. And check this kind of, yeah. And then, yeah, this kind of activity, yeah, sorry, will lead to restoration activity in the land. And also, I hope it lead to creation of environment from micro to macro scale. Yeah, yeah, sorry, a little bit time is past. Yeah, thank you so much. Okay.
Thank you, Dr. Taniguchi. I think you may have a question to him, but unfortunately, we don't have time, so I want to invite the final presenter. Yes. So please ask him directly. Yep. Right, thank you very much. For the final presenter is by Dr. Muraki. He is the president of CERA. He will talk on something about small DAC devices. Okay. Right? Yeah. Okay, so please start.
Right, so I'm going to talk about the development of a small CO2 capture device for educational use and democratization of direct air capture with a view to application and development to ECOS. So thank you so much for inviting me to here as a guest speaker, Professor Yamashiki. And my research theme is about direct air capture and also C1 chemistry. So my presentation is a little bit far from other presenters. But to capture carbon dioxide from ambient atmosphere is related to ECOS or further space explanation. So, okay, so let's start. And I'm Kazumi Muraki, president of Carbon Recovery Research Agency located in Odaiba, Tokyo in Japan. And so Carbon Recovery Research Agency is an independent research institute that aims to halt climate crisis and also to realize human migration to Mars. So we have a division of chemistry and also like the division for research in space sciences. And also we aim to convert carbon dioxide into useful fuels for like like for rockets and also ships and airplanes and so on. So we have a transportation division. So speaking of climate change, you know, as you know, climate change, we are in severe condition. In like a, it is an equivocal that human influence has formed the atmosphere, ocean, and land, according to IPCC's AR5 report. And we have to stop carbon emission right now, but we emit about 33 billion tons of CO2 every year, and oceans and forests can absorb only half of it. So 16.5 billion tons of CO2 we have to reduce or we have to recover from the atmosphere. So the drastic climate change measures are needed to achieve the 1.5 degrees target. So there are 3 measures against climate change. So the first one is adaptation, like a if we don't take any measures against climate change, like for instance, Odaiba in a waterfront area of Tokyo will sink because the rising in sea level, for instance. So we have to build large, how can I say, we have to higher the elevation of Odaiba in Tokyo waterfront area, and then we can live for another decades. And also for the second one, mitigation, is about the reduction of carbon dioxide. So we use like solar panels or like other green energy resources. We can reduce carbon dioxide, but like this, we have to reduce carbon dioxide by half. So adaptation and mitigation is not enough for measures against climate change. So we are tackling on climate engineering. What is climate engineering? So there are two major ways of climate engineering, and the first one is solar radiation management, or called SRM. So in the 1991, there was a eruption of the Pinatubo volcano in the Philippines, and it resulted in a global mean temperature drop of approximately about 0.5 degrees. So can we artificially reproduce this phenomenon and reflect light from the sun? There is a way to do that. So according to Dr. David Keyes from Harvard University, sulfuric acid aerosols could be sprayed into the stratosphere using aircraft or other means to control temperature increases. So if we do this on every flight, every international flights, we can reduce the temperature. We can reduce the sunlight, so that we can reduce the temperature of the whole world, like this. But the other way of climate engineering is, direct air capture, or called DAC. And direct air capture is a technology to remove carbon dioxide from ambient atmosphere, like by using amines or sodium hydroxide or potassium hydroxide, and so on. So here is the picture of direct air capture machine, and it is a carbon engineering DAC machines, but there is so many DAC startups in the world, like a Climeworks from Switzerland, and also Carbon Engineering from Canada, and Global Thermostat from the US, and so on, or Carbon Recycling International from Iceland. So we, CERA, started research on DAC for more than 10 years or so, and then most of DAC's machine is so large, one of the operator is missing, I think, but the size of human is like this height, so this machine is so large, and also it is so powerful to stop climate crisis. If Climeworks takes a DAC 36 plant, 36 means 36 units of DAC, and DAC 36 plant were to be spread over the Japanese capital, Tokyo, it would offset the global carbon emissions of only an area of Tokyo and parts of Kanagawa Prefecture. So the Kawasaki City and Yokohama City and Sagamihara City and whole Tokyo. We can stop climate crisis. We can recover 33 billion tons of carbon dioxide. So it's so powerful. But why is there so little awareness of DAC in Japan, and why are no DAC-related startups being established? CERA is was a only DAC startup in Japan. Right now, there are a few startups in Japan, but in 2017 or so, CERA was only DAC startup in Japan. So why is that? So we thought that the machine of DAC is so large and so complicated for general public. So we thought that we had to build a machine that anyone can easily remove carbon dioxide from the air by pushing only a button. So we built it. So this our tiniest small DAC device is named Hiyashi. I think it's so a Japanese anime-like name, I think, but Hiyashi, Hiyasu means to cool down in Japanese. So we made it. And Hiyashi is a very smallest DAC device, allowing anyone to easily absorb carbon dioxide with the push of a single button. And the method of CO2 recovery is chemical absorption, and various solutions such as sodium hydroxide, potassium hydroxide, and amines can be selected. And the key technology is the inside of this device. There are CO2 absorption cartridge, and then inside this cartridge, we could build a structure that maximizes the CO2 absorption rate. Like in major DAC devices such as Climeworks or Carbon Engineering's machine, the efficiency of carbon capture is about 90% or so. But for the smallest DAC devices, the efficiency is so worse, like maybe 0.1% or so when I started my research. But I've been working on this research for more than 6 years or so, and then we could finally realize 84% of CO2 capture efficiency. And also, we have a user's website, and then the user using Hiyashi can see the situation of carbon capture, like this graph. And also, we are tackling CO2 fuel conversion research, and I found in 2017 the reaction to convert carbon dioxide into methane by using a mechanochemical reaction with a collaboration of the University of Hiroshima. So in this research, the methane formation reaction from carbon dioxide and hydrogen, or carbon dioxide and water, by a single drop of water, was examined under two conditions. One using a hydrogen storage alloy, lanthanum nickel alloy, as a catalyst. It's a famous catalyst in this research. But I compared the aluminum foil, like you use in the kitchen, as a catalyst, And then we concluded that aluminum foil is useful for this reaction as so you can see here we could produce methane with an aluminum foil and also carbon dioxide and then single drop of water. Right, so that's all about my presentation. So thank you so much.
Thank you very much, Dr. Muraki. Very interesting talk. Question?
Thank you very much for your presentation. Actually, I've been watching you on YouTube talk about the feasibility on relocating to Mars. And that was really in a manner that your talk is very easy to understand and really fun to listen to. So so since you're conducting variety of research, so that I'd like to hear your findings from